YouTube connections also. So that is why we might face a little less crowd in today's
No
lectures.
problem.
Okay, well, so recording is going on. So it's that whoever has registered, they can access it remotely also.
Okay, very good. Thank you. Check. Can I start? Good morning. Today we will discuss about different techniques in fabrication of membranes in lecture 3 and lecture 5. And we try to introduce the famous fabrication method. There are many methods for fabrication of membranes, but some of them is more famous and more used. In this slide, you see the most used traditional methods. These methods have been used more than 100 years for fabrication of the mostly polymeric membranes. And we introduce these methods in this lecture. As you see, we have sintering, mostly used for ceramic membranes, nanofiber fabrication, track etching, stretching, and phase inversion. Phase inversion have been introduced by Loeb Sorirajan. Sorirajan was an Indian scientist that he lived in USA. And with help of Loeb from USA, introduced the phase inversion method that is a very simple method in comparison to other one for fabrication of the membranes. And with introducing this method with phase inversion, about 70 years ago, the production of the membranes is very progressed, and the price of the membrane is reduced. This phase inversion can be categorized to 4 main categories: thermal induced phase separation, phase separation or phase inversion. This is the similar phase separation or phase inversion. Thermally induced, named as TIPS, vapor induced, VIPS, evaporation induced, IIPS, and non-solvent induced, NIPS. Okay? When I will say NIPS, that means non-solvent induced phase separation. The first technique, that's very old technique, is the stretching technique. In the stretching technique, we use semi-crystalline polymers. We use semi-crystalline polymers such as PTFE, polyethylene, polypropylene, and we usually melt, not dissolve in solvent. We usually melt these polymers, and after melting, we produce a film or a fiber, hollow fiber, okay? And when we coat this melted polymer on the surface of a glass, the polymers should be reduce the temperature. And with reducing the temperature, the polymer solution changes to solid, okay? And changing of this liquid phase to solid phase is named phase separation or phase inversion. Phase inverse from liquid to solid, okay? Therefore, in phase inversion or phase separation, we have a liquid phase. Liquid phase can be from melting or from dissolving in solvent, okay? We melt the polymer or we dissolve a polymer in the solvent. In stretching technique, we usually melt, or if we have a dissolved solution, the concentration of a polymer is very high. And we have a very viscous solution. We coat on a glass or on a support or produce as a hollow fiber. And when began to the solidification, we stretch the new solid films. In nanofiber, we stretch with these rolls, with speed of these rolls, and in the flat sheet, the support is separate together and cause to the stretching of the film. When we stretch the film, as you see in this SCM image, when we stretch, the chains would like to separate from together and produce a free space. And this free space is pore of membrane, and this area is the body of membrane, matrix of membrane. Therefore, with stretching, we produce some porosity in the semi-crystalline polymers. The porosity is very high, the flux is very high, the pore size is big. Therefore, these membranes mostly is microfiltration. We cannot produce nanofiltration with this method. In this method, we have a big pore size. The second technique is track etching technique. In track etching, with using of the high energy radiation, such as gamma radiation, we have a concentrated laser or gamma irradiation, and we focus the irradiation on the previously prepared the film. We have a solid film, but no porosity. We have a dense film, and we put this film under the high energy radiation, and with the radiation, because of the high energy, the chains of polymer is destroyed. We have a long chain of polymer. With irradiation, we chop these chains. Next, after irradiation, we put the membrane, the film, in etching bath. Etching bath is a solvent bath that can dissolve the irradiated area. With irradiation, the molecular weight of polymer reduces in the irradiation area, and this area can be dissolved in solvent, and other area cannot. Therefore, with irradiation, we destroy some of the polymers in this area, and this area can be easily dissolved in the solvent, and other area cannot, and therefore we produce a pores. Here also the pores is big because we cannot very reduce the laser diameter. Mostly used for microfiltration, and we have a cylindrical pores. This is a special that we have a cylindrical pore. We can reduce the pore size in microfiltration amount. We have 800 nanometers. We can reduce the size, and the pore size is narrow. The next day, I say that, the previous day, I say that the similar pore size is good from separation and falling. In these membranes, we have usually the similar pore size, but you see that some cases two irradiation is near together, is close together, and cause to some big pores. But normally, all of the size is similar, and the fouling of these membranes is low comparison to the phase inversion. Usually, polycarbonate polymer, semicrystalline polymers used in this method. The third method, is sintering. Sintering mostly used for ceramic materials. In sintering, we usually have a powder, and with pressing the powder, we prepare a disc, a thin disc, prepared by high pressure pressing, but the stability of this disc, this film, is not suitable. And with a very low pressure, we can destroy and brittle this disc. For increasing of the stability, we should sinter the obtained pressed disc for attachment of the particle together. Sintering, that means we use high temperatures. For example, for alumina ceramic membrane, we use 1,700 centigrade. For silica, we have a need lower temperature, 1,200 centigrade. Therefore, we need high temperature for attachment and increasing the stability and strength of the membrane. In this method, we used powder of inorganic material or powder of polymer. We can also fabricate this disc with polymers. We put the polymers in the pressing and press the polymer and use low temperature in polymer sintering. In polymer sintering, we usually use 200 centigrades. But the resulted polymeric membrane is not good efficiency in this method, and we most usually for ceramic membrane fabrication. Also, we can fabricate the ceramic membranes as 2-layer, 3-layer, 4-layer. The commercial ceramic membranes usually have 3-layer, okay? And you see in the support layer, we have a big particles. The second layer have small particles. That means this small layer is selective layer, active layer, or separation layer, and these big particles act as a support for the thin layer. For both layers, we need to resintering. We first press and sinter the bottom layer. In the second step, we coat the second slurry on the surface of support, and again we re-sinter. Therefore, in the fabrication of ceramic membranes, we usually 3 or 4 sintering steps in high temperature, therefore need high energy production, and therefore the price of ceramic membranes is very high. By pressing of and sintering of this particle, between the particles, we can produce the pores. If the particle is small, the resulted pores is small. If the particle is big, the resulted pores will be big. With controlling of the size of powder, we can control the size of pores. Therefore, the sieving and meshing of the powder is important in ceramic membranes. Another process is electro-spun nanofiber membranes. We have a microfiber filters. Our microfibers used in cloths. We have a fiber with a diameter of 200 micrometers, 300 micrometers, 400 micrometers. This is a microfilter. Nano means that the diameter of fiber or particle should be less than 100 nanometers. in the definition of the nanotechnology, we say that every particle, every film, every fiber that have a dimension less than 100 nanometer, it is produced by nanotechnology technique. Okay? We have a microfiber filters. When we have a microfibers, the obtained pores between the fibers will be big, okay, and they will be filter, not membrane. For fabrication of the membrane, we must produce the fibers with very thin diameter, nanofiber, okay? But producing of the nanofiber from the needles that used in microfiber is very hard. And production of the needles with diameter of nanometer is very hard. And in the using of these needles, because there are some gels in polymer solution, the needles rapidly block it. But these gels, okay? In the preparation of polymeric solution, all of polymers not completely dissolved. Some of them not good dissolve and prepare the gels. The gel is particle. And these gels that we cannot see in the solution can block the needles, nanometric needles. For this reason, for reducing of the fiber diameter, electromagnetic is used. That means between the needle and the collector. Between the needle and the collector, we induce a very high voltage electrical field. And this high voltage stretch the microfiber to reduce the diameter. In this area, we have a microfiber produced. The produced microfiber between this distance, that usually 20 centimeter, this distance changes from microfiber to nanofiber with stretching by electric field. We prepare the polymeric solution, fill the syringe, and apply very low pressure for injection of the polymeric microfiber, and collector began to collect the fibers, and in this collecting, the microfiber changed to the nanofibers. And when we have the nanofibers, the free space between the nanofibers will be nano-size pore. And we can produce microfiltration, ultrafiltration, and nanofiltration with this method. Okay? The production of nanofiltration is very hard, but it is possible. We must control all of the parameters to reach the very nanofibers for production of nanofiltration membrane. We can easily prepare the MF and UF, but fabrication of nanofiber have some challenges. Usually, this system, collector and syringes, put in a chamber because we have a high voltage, and it can be dangerous. And we must use some equipment that do not conduct the electricity, and should be isolated. This is you see, this is this device, the syringe and the pump for injection. This is collector. Collector can be vertical or can be horizontal. Both design, there it is. You see this here. The high voltage. We can control the humidity of chamber. We can control the temperature. And I say that this distance between needle and collector usually between 10 to 30 centimeters. It is very low distance. In this distance, the liquid polymers should be changed to the solid fibers. Therefore, we must use the solvents with high volatile properties. That means the boiling point of the solvent should be low. Usually use mix of acetone with DMF, acetone THF, acetone NMP. Acetone, very rapid volatile. Therefore, usually mix of the acetone in this distance and with temperature, usually use 40 centigrade temperature in this chamber, and the produced nanofibers rapidly change from liquid to the solid state. The production in this method need high time, because we want to produce 100 micrometer thickness with nanofiber thickness, okay? We usually 2 hours need for production of a membrane with thickness of 100 micrometer. Therefore, we put the syringe with polymer and began the production and the nanofiber product, and 2 hours, 1/2 hour is need for completing the membrane, and therefore this technique is time consuming as is not rapid. In industrial scale, for increasing of the productivity and reducing the time, use many nozzles. In lab scale, we mostly used 3 or 4 needle, okay? But in the industrial, use 100 needles that simultaneously produce the nanofiber. But in industrial scale, we also need about 20 minutes for production of the membrane. But in the phase inversion, we need 1 minute. 1 minute, 20 minutes. It's very different. Therefore, phase inversion method is most industrial method because the production speed is very high. With the addition of any additive, any nanoparticles, any new monomers, new polymers to the polymeric solution of phase inversion or electrospin, we can produce the, for example, nano-composite membranes. In this paper, silver nanoparticles were added to the casting solution, to the dope solution, to liquid polymeric solution, and the produced nanofiber, you see, have different morphology, and the silver nanoparticles mixed and decorated on the fiber surface and cause to antibacterial properties to the membrane and reduce the biofouling of the membranes. But the most used industrial method is phase inversion or phase separation technique. As I said, in the phase separation, we first produce a liquid polymeric solution. And with change of this liquid solution to solid film, we produce the membranes. And the change from liquid to solid is named phase inversion or phase separation. Of this change from liquid to solid, mostly done with non-solvent, vapor, evaporation, or thermal. For technique, for change liquid to solid. Non-solvent, polymer, dissolve in a good solvent. But if the polymer is not dissolved in another solvent, the another solvent is non-solvent. Okay? Polymers is dissolved in organic solvents, like as dimethyl acetamide, dimethyl formamide, methylidene prolidone, and others, but do not dissolve in water. Okay? Do not dissolve in ethanol. Therefore, ethanol, water, is non-solvent for polymers. And when we add drops of polymer in the non-solvent, rapidly produce a circle particles. We use these methods for change of liquid to the solid films, and in this step, with control of conditions, we can produce porous or non-porous membranes. Both porous and non-porous can be produced. We can produce spongy membranes, finger-like membranes, and others. All of the membranes can be produced with phase inversion technique by controlling the conditions. In lab scale, for production of the thin film layer, we usually use this device. You see it, have a different configuration, structure. And we say applicator, doctor blade, or knife. In the papers, you see that say that I cast, this coating is called mostly casting. I cast the casting solution, the dope solution, the liquid polymeric solution, on a glass or on a fabric using doctor blade with thickness of 200 micrometers. Okay? This device can coat the micrometer layers on a surface. Surface can be glass, fabric, or every plastic surface. Every surface we can coat the polymeric membranes, but we usually use glass, fabric, and plastic films. In this applicator, with this, we can control the thickness of the film coating. When we open, this area go to the up, and the thickness increase. With closing, go to the bottom and reduce. But this device have a constant thickness. This have a 4 area, and each area have a distinct thickness. For example, the bottom is 100, the right is 200, top is 50, and the left is 150 micrometers. The use of this is easy, and the long time of use is high, but this may be destroyed and need to the repair. This is also have a 4 side, and every side is the specified thickness. For coating of the casting solution with these devices, we usually use this device. This device have a specific speed. We can control the speed of casting. We can cast with my hand, put the polymers and cast with hand. But the speed of hand may be different from one person to another person. And this casting speed is important. Therefore, it is better we use a speed control casting. That we put this one here, put the polymers here, and we coat the layer on the membrane surface. We have a video, a possible play video. Video 1. This is my lab in Iran. My students want to prepare a flat sheet membrane with this device. The glass, this is the applicator. We prepared a casting solution. You see the viscosity is like the honey. With controlled speed here, we cast and rapidly transfer to the non-solvent. Non-solvent is water. Contacting with water, the polymer, the liquid thin layer, rapidly change to the solid one. And after 30 seconds, the membrane is ready. During the phase inversion, in this step is very important. The solvent exists from the polymer, and instead of it, non-solvent go to the polymer solution. This existence and entrance produce the pores. The entrance of the non-solvent into the film layer cause to the pores, cause the porosity. The polymers do not like the water, and they want go out from the water. They do not like to close off the water, and therefore with the inserting of the liquid polymeric membrane to non-solvent, rapidly all of the chains want to get out from the water and collect together, and when they collect the chains, then they will be solid. Liquid have a free movement, but when all can collect in one place, the change from liquid to the solid will happen. The general schematic of the membrane preparation, flat sheet one, shown in this slide, we must first prepare a dope solution or casting solution. For preparation of this solution, we need solvent and a polymer. A polymer that should be dissolved in solvent. This dissolving mostly need 1 day after addition of polymer to solvent, and mixing, usually we need 12 hours, but in the lab we use 24 1 days for completing dissolving and reducing of the gels. I say that some polymers cannot be dissolved and the gels. During this styling, maybe some air, some gases will be inserted in this solution, and this gas causes to the defect in the membrane, and during the fabrication we see that some pores, visible pores, there is in the film, and this due to the gases in the dope solution. Therefore, after complete dissolving, we 1 day again without stirring. Keep the solution for degassing, or use an oven for degassing. We close the dishes of the dope solution and put it in an oven for 6 hours in 50 centigrades. The high temperature reduces the solubility of gases in liquids. Okay? After 6 hours, we get out from the oven and began to fabricate the membrane on glass or fabric. And after the coating, we put them in the non-solvent. Organic solvent exists, and non-solvent enter to this layer, and this exchange between the solvent and non-solvent cause to the pores. The exchanging rate is very important, exchanging rate. If we have a high exchange rate, rapid entrance, rapid exit, we will have small pores. Rapid exchange, small pores. If we have a slow exchange rate, we will have a big pores. Okay? Therefore, with controlling of this speed, entrance and exit, that's called exchange rate, we can control the pore size of the membrane. We can produce microfiltration if there is slow exchange rate. For nanofiltration, we must increase the exchange rate. In industrial scale, I showed yesterday the film. This device is used. The process similar, but the device is different. In this case, in this area, we have a ductor blade and solution. by rotating of this roll, that on the surface of this roll we have a fabric. Fabric come from the bottom of the ductile blade, and a thin layer of the polymeric solution coated on the fabric. In industrial membranes, we used fabric always, because a fabric increase the strength and stability of the layer. But in lab scale, no necessary for using of the non-woven fabric. After coating, rapidly go to the gel tank or coagulation tank or non-solvent tank. In this step, 10 seconds, the liquid film changes to the solid film, and go to the rinse tank. In this rinse time, about 5 minutes, the membranes will be in the water for complete exchanging of solvent with non-solvent. All of the membrane pores produced and will be filled with water, with non-solvent. After that, they take off, rolling, collect the prepared membranes. We can control the non-solvent with temperature and other parameters for producing the good membrane. You see that the process is very easy. The process, we prepare a solution, cast, and in a non-solvent, we produced a membrane with high speed. But the controlling of conditions is very, very important. And we have a very errors. We prepare a similar solution, and I give this solution to 2 students. And each student prepare with the similar device, similar non-solvent, all is similar. Only student is changed. And after fabrication of the membranes, one student flux is 100, the another one is 300. Many, many errors. You prepare a membrane, okay, one sheet, and cut 2 circles for testing. This circle is 100, this circle is 200 flux. In one sheet, all of method, all of solution, every is similar. But the flux and rejection is different. It is the problem of the phase inversion. The phase inversion method is very good, but fabrication of a uniform membrane is very difficult. From one day to another day, the membrane is changed. Today, we have a high humidity, and tomorrow, low humidity. The humidity of the air in this casting is very important. The humidity is water, okay? Water is non-solvent. The humidity of the weather in this casting can cause pere-solidification. The humidity caused here during the casting cause the solidification. We cannot see, but happens. Therefore, the humidity, the temperature of air, and many, many parameters is important. The speed casting, one student rapid, one student is slow. It's very important. We have many errors, and therefore we must control these conditions. Please, video 2. Some companies can suggest their devices for fabrication of membranes. There are many videos in YouTube. You can see them. This is a device in lab scale for production of the membranes on the surface of the glass. This is a coagulation bath filled with non-solvent. That here is water. This device has software that controls the speed of the casting. This is the applicator which can change the thickness. You see, the thickness is controlled with digital system, not with hand. Here also controlled with hand that show that our system can be digital controlled and with hand also. Casting solution. This chamber is oven and can control the temperature or can control the humidity. I discussed non-solvent and I mostly discussed about NIPS, non-solvent induced. The second method in phase inversion is IIPS, evaporation induced. In evaporation, after the coating, we do not use non-solvent and cause the obtained films in the contact with the weather or in an oven for evaporation of the solvent, okay? Evaporation phase inversion. In this evaporation, we have non-porous membrane. IIPS, evaporation induced, used for production of non-porous. For example, for protein exchange membrane. In the fuel cells, we have not used NIPS. We used IIPS, evaporation after the casting the films located in oven with control of humidity, control of temperature, and began to evaporation of the solvent. After evaporation, a solid layer will be produced that used in gas separation, in perovaporation, in exchange membrane. That in this type of membrane, we need non-porous membranes. These images is taken during the phase inversion with the microscope and photographer, okay? You see the time. I said that the phase inversion is very rapid phase. You see that during 2 seconds, the pores will be produced. In this area, okay, you see this boundary. This is a polymer solution. Here is water solution. When the water and polymer solution are contacted together, the water began to diffuse. Diffuse in the polymer solution, and in diffusing, produce the pores. You see the road of the diffusing, and this diffusing produce this finger-like pores. And in diffusing rate, our exchange rate is important. For example, in the right photographs, we have 3 different polymer solution. The polymer is similar, polyether ether ketone, but their concentration is 12, 10, and 8%. This, with increase of the polymer concentration, the viscosity of the solution increases. Therefore, the increase of viscosity reduces the diffusion speed. Therefore, you see in this area the similar time. For low viscous solution, the pores is rapidly produced, but for the high viscous solution, the diffusion rate is low. Okay? Therefore, in these photographs, we can see the phase inversion process is very rapid, and the exchange rate that can be changed by solvent type, polymer type, temperature, polymer concentration, and many other properties that okay. There are 16 parameters should be controlled in fabrication of the phase inversion membranes. Phase inversion membrane can be fabricated as hollow, tubular, or flat sheet. No important. The mechanism is similar. Only the configuration of membrane is changed. We must control these 16 conditions. And with change of every of these conditions, the properties, the flux, the rejection of the membranes will be changed. We have a 3 step in the fabrication of the membranes with the NIPS method. We must prepare a casting solution, condition of film casting, or tube casting, or hollow fiber casting, and composition of the coagulation path. We prepare casting solution, cast, and cause and immerse in the non-solvent path. We have 3 steps. And all of these 3 steps is important. We have a 3 temperature of casting solution, temperature of casting medium, and temperature of coagulation bath. We must control 3 temperature. And we know that with the change of temperature, the kinetic is changed and the diffusion rate, exchange rate can be influenced with temperature. Polymer type, with change of polysulfone to PVDF, the membrane is different. Polymer molecular weight, very important. Solvent type, concentration of the polymer. Additives, we can additives to the solution. Performer, we can add performer. We can add photocatalyst. We can add antibacterial agent and different type of additives. The thickness in the casting, the thickness is important. Humidity of medium, the casting speed, evaporation time in air. When we cast and put it to go to the coagulation bath, we have a 3, 4, 5, 6 seconds between casting and immersing in non-solvent. One student rapid in the 3 seconds, another student is slow and 10 seconds between the casting and immersion. Therefore, this contact with air is very important, and this is the main reason for change in flux with change with student. Support type, the glass, the plastic, the fabric is also influenced on the membrane flux. Usually, the membranes on the fabric support have higher flux from the glass. When you cast in the glass, flux is 200. When you cast in the non-fabric, 2 times, 3 times, the flux increases. And the type of the fabric, non-woven fabric, is also important. The non-woven fabric density, pore size is very important. In the coagulation bath, the non-solvent type, added polymer solvent to bath, we can add 5% the solvent to the non-solvent. With addition of the solvent to the non-solvent, the exchange rate decreases. The exchange rate, when we add the solvent to the non-solvent, the non-solvent will be similar to the solvent, okay? When we add the solvent to the non-solvent properties of the water will be reduced. And this reduce the exchange rate and the pore size of membrane will be increased. We can add additives to the bath and other properties. Therefore, phase inversion is very easy method, but we must control all of these 16 conditions, and control of the all condition is very hard. And in industrial scale, we need to clean rooms, the chambers, the closed chambers. We need to sensors for detect of these changes. No, mostly, I speak about flat sheet, but we can produce the hollow fiber membranes also. The time is finished. 1 hour is finished. But my slide is this number. I speak 10 minutes and continue in lecture 5. Okay, Prof. Laka? In the fabrication of hollow fiber membranes, instead of applicator in flat sheet, we have a spinneret. We have a spinneret. A spinneret acts as a applicator, Dr. blade in flat sheet. In spinneret, this is the actual picture. We have this structure. You see, when we open this device, the spinneret have different sections that you see a needle. This better shows. This is the spinneret. We have a polymer solution inject to this needle. Okay, but we want to produce hollow fiber, tube, not fiber. In production of fiber, we have not this central tube. We have only have this needle. But we want to produce a tube. And for this purpose, we used a non-solvent in the spinneret. And we first coagulation inside of the spinneret. Okay? We have inject this solution from here, but as injected in this place will be contacted with non-solvent, and we have solidification here inside of the tubes. This water, this bore fluid, we say bore fluid. Bore fluid will be inserted in the spinneret inside of the tube. And after the production of the tube, directly go to the coagulation bath, and the other process is similar to the flat sheet. We have a coagulation bath, non-solvent, and we have a washing bath and take-off roll. Okay? Therefore, inside of the spinneret, we have a bore fluid that usually is water, or water containing NaOH, caustic water, that this NaOH increase the solidification. And after production, we take off on the roll. Therefore, we produce the tubular hollow fiber that have entrance and exit area. Usually say to the inside of the hollow fiber, lumen area. Lumen area, that means the inside of the hollow fibers. And we have a selective layer. In the flat sheet, we say that top layer is selective layer and bottom is support. With control of conditions, we can produce the selective layer inside or outside of the membrane. With control of bore fluid conditions or coagulation bath conditions, we can produce the selective layer inside or outside. Okay? Based on this control of conditions, the feed can be in outside to in, out to in, here, outside in, or inside out. The feed can be inside of the tubes, or the feed can be the outside of the feeds based on the selective layer. Thank you for this lecture. If you have questions. Yes.
is in the non-solvent induced phase inversion technique, is the solvent affecting the choice of the solvent affecting the property of the membrane, obtained at the end.
Yes, yes. With change of the solvent, polymer solvent, the properties of the membrane can be changed, and the solvent is very important because with change of the solvent, the chemistry of the liquid solution can be changed, okay? As you see in this slide, every parameters is similar, only the solvent changed from dimethylformamide to a methylpyrrolidone. With change of the solvent, the chemistry change, the viscosity of the solution change. For example, in DMSO solvent, we have very viscous solution. In NMP, we have a low viscous solution. As you see in this slide, with change of only the solvent, the morphology of the membrane changed from finger-like to the macrovoid structure. Okay, the solvent is very important because that influence on the exchange rate.
Okay, thank you.
If I want to prepare a composite membrane,
Yes.
then how to add?
Yes. I will discuss about nanocomposite membranes in the tomorrow section about composite. For fabrication of the composite membranes, we have a different method. The simple method that we add nanoparticles to the solvent, and for good dispersion, we use ultrasonic radiation. Ultrasonic good disperse the nanoparticle, and after good dispersion, we add polymer and let to dissolve complete. It is the simplest method, but we can add a coating layer, we can spray the nanoparticles, and different methods.
Thank you.
I will discuss tomorrow.
Can it be possible that in case of a Dr. Blade method, the coating that we're doing,
Yes?
and goes on adding different
Layer?
layers?
2 layers, yes. We have devices that coat 2 layers continuously. Between the first Dr. Blade and second Dr. Blade, we have a 5-6 centimeter distance. First 1 layer coat and next second layer. We called dual layer membranes. In the preparation, and in some cases after the preparation of the first layer and drying, we can use the membrane as a support, and second layer will be cast on the solid first layer. There are many methods for production of the dual layer, 3 layers from polymers. Ceramic layers, ceramic polymer membranes have 3 or 4 layers, but UF, MF membranes usually is 1 layer. But some Nafion membranes have 2 layers. When we see the cross-section of Nafion membrane, we see it is 2 layers. Our RO membranes have 2 layers, 1 thin layer and 1 thick layer. But we have dual layer, have 2 different polymers can be coated.
So how one can be assured about the binding of 2 layers if it is being formed?
When we cast the second layer, for example, on solid polymer, the solvent of the second layer can be dissolve the support layer and produce an adhesive. And this causes to increase the stability. Okay? So because the solvent can be dissolve the support layer, and this dissolving act as a adhesive. All of adhesive is a polymer and a solvent. And this solution can attach to the many surface.
Sir, actually I have used YSZ, yttrium stabilized zirconia. Over that I have casted nickel oxide. but I faced that my tapes were broken. There were cracks over the tapes. So
And then repeat your question.
Yttria stabilized zirconia was the main support over
Yes.
which I casted nickel oxide.
Yes.
So, but the way you are saying, no, over another we have to cast. But I have seen that there were some cracks over the nickel oxide. My tapes were spoiled.
For cracks in the membranes, we have a different methods for reducing of the cracks. The defect or cracks caused to reduce the membrane performance. In gas separation, for example, use polydimethyl siloxane as a defect filling layer. Okay? When we produce polyimide gas separation membrane, maybe because the polyimide have a semicrystalline, maybe we have a defect. In this case, we use the sealing agent.
Yeah, sealing.
Sealing agent, reducing of the sealing, we use very, very fine powder. When we have a big pores, big defects, with using of a thin layer of the very fine powder as a force layer, we seal these cracks, okay? And mostly named as protective layer. We also, in fabrication of most TFC membranes for gas separation and RO, after preparation of membrane, we coat a protective layer on the membrane surface for reducing the defect in modulation. When we module and produce the envelope, maybe the surface of the membrane can be harshed and can be defect, okay? Therefore, we use a water-soluble protective layer on the surface of RO membranes, for example, polyvinyl alcohol. And when we produce the module, during the test of the modules, the polyvinyl alcohol will be dissolved in water, and after 2 days, 3 days, this layer completely removed. Therefore, the sealing is very important in the membranes. Okay? No question? Thank you.
Thank you. Thank you so much for your lovely talk. And it is really a very visually attractive and very informative. And I think our audience has benefited a lot from the insights that you have provided. And I can see from the interaction that happened after this that they are really interested and they have really learned a lot. So now what we will do is that we will proceed for a short tea break. After that, we will be joining here in the in this same room at after 5 minutes, after 10 minutes. Okay. So just one announcement is that after this talk, there will be a hydrogen energy level talk for 1 hour, and after that there will be another lecture followed by Professor Bhatanpur. Okay. Thank you. So 312 for the tea. Can I start? Okay. So welcome back, everyone. Today in this session we are going to talk about the storage of hydrogen. Now, when we are coming to the hydrogen energy sector, we require a few sequential steps. First is obviously that we need to generate the hydrogen. In A studies class, I talked about the electrolyzer system. Electrolyzer, what does it do? It generates the hydrogen. Now, if we want to have a more greener solution, we can have a renewable energy like solar system to generate this hydrogen, this electrolyzer. Now, after that, we need to use this hydrogen. So, is it always possible to use the hydrogen where you produce? No, it is not always possible. So, in that case, what you can do is that you might be requiring to transport this process from one place to another place, or you might be requiring that maybe you are producing the hydrogen at a certain time of the day, maybe you need to generate the electricity at a later time of the day. So, you need to store this hydrogen. So, that is why this storage comes in picture. So, so that the hydrogen that you store, you can use it later for the application purpose. Now, for application or to generate the electricity from the hydrogen, hydrogen is nothing but a fuel here. So, to generate the electricity, we need a fuel cell. Now, this hydrogen, the storage of hydrogen is particularly very challenging, and in that case, we are going to see why it is challenging. We all know that hydrogen comes at the very beginning of our periodic table. So, now that is why the density of hydrogen gas is only 1/10 of natural gas. It is very low. Even the liquid hydrogen, that is also very low density. But the problem is that with the low density also we have the advantage of this hydrogen is that we can have a much larger amount of energy per unit mass, that is 120 megajoule per kg for hydrogen, which is 3 times of the gasoline. So, per kg of gasoline we can get huge amount of energy, we can get 3 times of that of gasoline, but how is the volume of this per kg of hydrogen? That is also very huge. So, we need a huge container to, if we want to store it in a gaseous form or in the molecular liquid form. So, that is why it is very important to store it properly. Why it is also very important to keep the safety aspects in mind? Because we know that hydrogen is extremely flammable, and if we catch fire, the flame velocity is 346 centimeter per second. So, if there is a hydrogen fire here, in a second it will go 346 centimeter. So, it is very fast, it is 8 times of that of methane. So, the fire will progress very rapidly if there is an accident. Okay. So, that is why we need to keep that safety in mind while we are storing the hydrogen. Now, we are going to see what are the methods that we store hydrogen. Now, for storing hydrogen, I already told that we need the hydrogen storage for intermittent use or for transport from one place to another place, that is the purpose of storage. Now, the types of storage are mainly of 3 different types. One is the physical storage. In physical storage, what do? We just keep the hydrogen in its own form. So, we make the temperature very low or the pressure very high, so that it can keep it in the physical form, in its own form. In chemical storage, we make a complex or a conjugate with another compound and we store it. In a membrane based storage, what we need is that it is very often to find from natural sources or from other sources hydrogen gas mixed with some other gas. So, what we do in membrane based storage mainly is that we store that mixture of hydrogen gas with other gas, and whenever we require this hydrogen energy, we use the membrane to selectively transport the hydrogen energy from one side to another side. So, here the purpose of the membrane is that we do not have to convert the hydrogen in another form, whether in a liquid form or in a conjugated form, but what we do is that we transport these from one place to another place by help of selective transport mechanism. Now, here what, as I was telling that let us see a little more details about these three types of storage. Generally, it is stored in physical storage in the molecular form. Typically, the pressure requirement is very high, 350 to 700 bar. So, you can understand, because this hydrogen is so light in nature, so that is why we require very high pressure and very low temperature also, minus 250 degrees centigrade, to store it as a liquid. So, you can imagine the amount of mechanical energy you require just to store this hydrogen in a physical form. Now, the chemical storage is what? It can give you a metal hydride format. I will just try to take the help of this metal hydride. So, metal hydride, what they do? They go through a cyclic process of absorption and desorption. So, in the absorption slide, what we are doing in the absorption cycle, this metal, they just conjugate with the hydrogen molecules, and at the hydrogen molecules attach themselves surrounding the small particles of the metals. That is the metal hydride. And now, when we change the temperature of the system, just by altering the temperature of the system, we can switch between absorption and desorption cycle. Then we can go from this hydrated to the non-hydrated sample. So, we can get the hydrogen out of the system. So, we need to switch the energy, the temperature of the system. So, that is a part of the chemical storage system. We can use metal hydride, which is more common in a chemical storage, or we can use liquid oxygen carrier, liquid hydrogen oxygen carrier. What are those? Basically, they are stored in form of ammonia or methane, this kind of format, a different chemical form. And if you need to change the ambient condition, then you can release. So, basically, here you need to produce a chemical reaction in order to release this hydrogen. So, in this system you need to produce a alternate chemical reaction. That is why we have this kind of complexity in the chemical reaction storage. Now, that was about the chemical reaction storage. In the physical reaction storage, you can compress it to a very high temperature, very high pressure, and to a very low temperature process, or you can have it compressed with the cryogenic storage option. Okay. So, we have given here a few options of this storage system, the physical based storage. We can have compressed gas in a very high container, very highly sealed container. Also, we can have it in a cryogenic container like this. Or otherwise, if we are having a material based, then we can have it in form of MOF or adsorbent, or liquid organic or industrial hydride, etc. So, these are the options which are more common, or chemical and physical storage. Now, as I was telling that getting gas stream with hydrogen gas mixed with other gases, that is very commonly found in industries and natural sources, and for that we can very cleverly we can use membranes in order to utilize these hydrogens. So, how do we do is that, let us say that I have a mixture of carbon monoxide and hydrogen, I have a palladium membrane. When this mixture comes in contact, these hydrogen molecules, they get dissociated with H and H plus, and then they get transported through the membrane. Okay. So, this is practically allowing only the hydrogen, not any other molecule through it. So, on the other side, or the permeate side, or the downstream side of the membrane, what we are getting is a hydrogen gas. So, this is what is one of the typical application of a inorganic membrane, inorganic metallic membrane. We can have some specific polymeric membranes, but very dense structure. As in the previous section, in the previous lecture we were listening to various kinds of
phase inversion and membrane preparation technologies. Sir was mentioning about the when we are making gas separation membrane or membranes for this type of application, we do not expose it to the water or non-solvent. What we do is that we do evaporation of the solvent for this polymeric membrane, so that we can have a very dense structure of the membrane. What are the typical conditions where when we are having this kind of polymeric membrane? So we can have it exposed to a vacuum. Vacuum will do the evaporation of solvent very fast, and also we can do the do this evaporation of solvent in a inert atmosphere. Okay. So just keep in mind that if we want to have a very dense structure, if we want to have a polymeric membrane for this kind of application, we want it not to be prepared by a non-solvent technique, but to be prepared by a solvent evaporation technique. Okay. So this metallic membrane and polymeric membrane, this can be a very cost effective solution, but at the same time it offers a lower selectivity. Ceramic membrane, we know that it is a very high temperature operation. So we can go for very high temperature operation with these techniques, and the advantage is that you can get almost 100% pure hydrogen if you engineer the membrane accordingly. So you can have very low energy consumption, because again you are not creating very high pressure, you are not creating very low temperature. So these conditions when we are getting rid of, then energy efficiency goes up manifold. Okay. So it is also very compact and stable, because we have less amount of mechanical components through it. Okay. So if we compare the compare these membrane based storage with other conventional storage, one thing we can see is that I was telling you about the polymeric storage. So whatever preparation method you use, still it is less selectivity is less compared to the inorganic membrane if we have a polymeric membrane. So you can have some other options like MOF or other adsorbent if you just impregnate as a form of a composite material, as a form of a additive for your polymeric membrane. In order to that, you can increase the enhance the separation efficiency. So it is preferential transport of hydrogen which is being used in a membrane based technology. So much lower energy consumption. In the hydrogen purity level, you can go manifold. So you can get the means almost 100% purity with this kind of membrane storage system. You can use lighter materials also like graphene or MOF as a membrane material, but when we are having a cryogenic hydrogen storage system or a liquid hydrogen storage system, there are a lot of auxiliary components adjusted. Okay. So that is why it can be lighter. Operating pressure, as I already told, it is lower. Now thermal stability is also comparatively higher, but compared to this we need to be more careful, because there are certain components like MOF which will degenerate if you go up to very high temperature. Okay. So that is why we do not need very high temperature, but we need to be very careful with the temperature level. But safety is that there is one problem with this conventional storage, or one challenge with the conventional storage is that because we are using a very high pressure operation, so that is why in case there is a leakage in tank or anything, then the accident goes very huge, spreads very fast. But if we have a lower pressure requirement like in membrane, obviously you can have a lower risk. Okay. So, but one thing is that today we need to focus more in today's scenario to make these options more flexible or more economic. Okay. Now, as we know that membrane is practically selective transport. So, it is blocking other gases, it is only allowing the hydrogen, but not allowing the CO, okay, or CO2. These kind of materials are not being allowed to pass. That is the mechanism. Now, what is the mechanism of transport? what through which this mass transfer happens. In yesterday's class sessions we were talking about the diffusion, solid diffusion, and also we can see that we have talked about in the RO what kind of mass transfer happens. So, here we can see both types of diffusion, active and passive transport, both kind of diffusion. What is active transport? Active transport is like hydrogen itself is getting diffused through the molecule. What is passive? Passive is that it is getting itself attached with another molecule, and that molecule is getting transported and separating hydrogen on the other side or the downstream side. So, that is all kinds of transport selection activity appears. But now again, what type of polymer or what type of membrane material you are using, that is important for optimizing the material or optimizing the operating condition of your system. Okay. So, now let us see that what form the metallic membranes offer. Okay. So, in the previous slide I was talking a little bit about the polymeric membrane. In the metallic membrane what does it look like? Mostly the metallic membrane used in the industrial or real life scenario, they are of ceramic in structure. So, what we see is that we have hydrogen and helium gas going through one side, and then they can diffuse through these metals and go in an atomic form and go to H2 form on the other side. So, these red, the molecular form is divided in the atomistic form, and on the other side it is going again to the molecular form to get the hydrogen energies, hydrogen in a molecules. So, now we can have palladium or palladium alloy in order to reduce the cost of the system, or some non-palladium metals like nickel, vanadium, etc. They can also be used for this type of operation. Now, let us see a little bit. So, this thing I already told you that when the membranes are selectively transporting hydrogen molecules, they are going through adsorption and dissociation first. So, these molecules, this is a mixture of CO2, CO and hydrogen. When they are getting in contact, then adsorption happens and dissociation happens, means H that happens. Then ionization diffusion, that diffusion can be active or passive. Desorption and recombination is that these are getting in a molecular form. So, this is the transport mechanism. You can have very high purity level. Now, let us see how they are rolled, how they are making the, how they are made these kind of membranes. So, now in this structure you can see that you can have a porous support, a stainless steel ceramic support onto the membrane, onto it you can have a palladium loading. So, what you do is that you can have two rollers rolling in opposite direction and pass a sheet of steel or support system through them, and onto these rollers you can have this palladium getting, and you can have it etched onto the surface of this support system, so that you can have a coating like this. So, now one thing, as I was telling you that palladium membranes are very popular nowadays in type of hydrogen energy. So, all types, all stages, preparation, storage and application, all these stages hydrogen is very popular. But one thing we have to be careful about the reaction with sulfur. So, we have to control the reaction with sulfur so that it does not pollute our membrane, or we do not lose the efficiency of the membrane. Okay, not only sulfur, it is also corroded by carbon monoxide very effectively. Okay. So, challenges and solution, as I was telling that you can get very ultra high pure, but at the same time they are used and in terms of fuel cells and energy, etc. One more thing that you can have with the membrane is that ceramic membrane. So, we have till now seen about polymeric and metallic membrane. Now, what are the ceramic membrane? Ceramic membrane is basically used whenever we need a very high temperature operation. So, like zirconia, alumina, silica base, they have a excessive very good thermal resistance. They allow selective permeation of energy. So, here in this system we are seeing that there is a catalytic conversion. So, what we have here is that we have a membrane, over it we have some catalyst converted, and here we are basically storing hydrogen in terms of other chemical compound here, and when we are in the lumen side, inside the membrane core, we are allowing the hydrogen, and here see this organic molecule we are allowing. On the catalyst side, we are getting the hydrogen separated, hydrogen and carbon dioxide separated. So, this is basically one of the example when we are using ceramic form of the membrane in order to this reaction requires very high temperature operation. So, this is practically one of the storage system where the hydrogen was stored in another form like in organic material. Now, they are in this particular paper they have reported that you can use this type of membrane for easy transportation or easy storage. So, you do not have to use hydrogen in its molecular form. So, you reduce the risk associated, but at the same time you can use the membrane. But at the same time this membrane efficiency is very high only when you use very high temperature, and so that you need a ceramic type of membrane for this operation. Remember, there is a catalyst coating onto the surface, and that is enhancing the transport, or that is enhancing the separation or generation of hydrogen through this scheme. Okay. Now, you can have, in order to enhance the properties like permeability etc., you can impart some of the other additives into the system to make it a composite materials like microporous ceramic membrane or dense ceramic membrane, so that you can have we can have more selectivity or more stability of these membranes. Okay. Now, in this course we have been very often talking about composites. So, composite, what is the role of composite? Why do we use composite? We already have so many options already, the metallic, non-metallic etc. But if we see each and every type of material, they have their own advantage and disadvantage. Basically composites are taking the advantages together. So, that is the role of the composite. So, you can integrate polymeric, metallic and ceramic layers. You can either have it layer by layer assembly. So, one thing that is one possible scenario is that we can have this kind of membrane, like say this is a matrix of polymer. You can have small materials impregnated like this. So, this is dispersed phase of additives, or you can have layer by layer assembly, you can have 2 layer, you can have 3 layer. So, layer by layer assembly is that is how you can have a composite. So, that is why these layers are made up of different materials, and they are enhancing the mechanical stability, they are enhancing the thermal stability by using this composite approach. Now, these composites can be of polymeric metallic or ceramic polymer or multi-layered composite membrane etc. So, they can be engineered very effectively to improve mechanical strength, utilize. So, one thing we have to be very sure about when we are using any kind of operation like this, that we are not the membrane materials are not leaching out from the membrane. Okay. Whenever we have any composite, not only for gas purification but also for liquid purification, during this operation, during the operation process, if the membrane material leaches out from the treatment, then the membrane efficiency goes down. So, we while characterizing the membrane, while making a new membrane, we always test the stability or whether it is leaching out. Those things are very important. Like, I would like to say about one particular system here. So, we all know that there are these membranes like Nafion or PTFE membrane, they are very, very popular. Now what many researchers all over the world they are now doing is like they are taking polymers like Nafion and they are making some additive like say metal phosphate or carbon nanostructure like carbon nanoanion or graphene. They are very popular additive as a choice. So they are inserting those into this material. Now yesterday I was talking with you about the water channels. Now what these additives are doing is that they are not letting these water channels to collapse at higher temperature. So you can enhance the thermal stability of the membrane by incorporating this kind of additive into your system. Now let us see that when beginning this lecture I told you about that when the hydrogen is stored in molecular form, we have physical and chemical and three distinct categories I told membrane based. But membrane cannot be used in these physical and chemical categories. It is not so. Membrane can be used in physical storage and chemical storage also. Okay. So in physical storage, how can we use a membrane or where the membranes are used in physical type of storage is that what we are showing here is that one liquid hydrogen tank which is developed by or which is used by Airbus. Okay, Airbus, even we all know that it is a very famous aeronautical company. So what they do is that they have a hydrogen container and they have to seal it very effectively. Okay, so there are many heating and cryogenic arrangement all throughout the system. They are developing they are insulating the whole tank very effectively. But now where is the membrane here? The membrane is basically at the outlet sector, okay, outlet sector. So what they are doing is that they are allowing at the side in this Airbus membrane, they basically use palladium type of membrane or you can have other options like polymeric or ceramic or graphene based membrane which are used by other companies. What they use is that instead of, why palladium is there, instead of having 100% pure nitrogen, you have a option to store, hydrogen mixed with contaminated with other gases or mixed with other gases like hydrogen nitrogen mixture or hydrogen carbon dioxide mixture, etc., which are more commonly found, and they do not require that much of high pressure or that much of low temperature, so that you can reduce the energy component, energy requirement of this surrounding material. Okay. Now this outlet pressure, this outlet channel, if you have a palladium component or palladium membrane here, but you cannot use the hydrogen mixed with other gases. So in order to get the pure hydrogen format, you have to separate out the hydrogen, but you have to selectively use the hydrogen sources rather than at the outlet sector. Okay. So even this kind of system is being tested in NASA also. So that they are so much promising and they are very, very useful for hydrogen transport and distribution system, so that pipelines and tankers can be easily maintained with this kind of technology. Now in the composite materials, as I was telling, that we have options like zeolite, metal organic framework or covalent organic framework. They can be nanostructured or they can have a performance considered for the, now these are some options that we can have, is that this zeolite is one of the very popular option for storage of hydrogen. You can have MOF also, you can have graphene based materials also to be inserted into your polymeric or ceramic membranes. But what are the factors that you should be keeping in mind before choosing the material that is that you can use in your composites? You can have very high selectivity, you should aim for a selectivity like 100%. The membranes should be very much durable. Okay, so for that zirconia has been proven to be offering very high durability. So the permeability should be also high. So when you are making a composite, it should not happen like that the hydrogen gas which is coming out of your system, that is coming at such a slow rate that it is not useful for your application. So that is why permeability should be high, and for that graphene oxide has been chosen to be, or graphene oxide has been proven to be very useful in this technology. Okay. So now what are the options that we have for enhancing the technology, enhancing the system or enhancing the performance of the system is that you can have different MOFs being engineered all over the world, different structures of the MOF. You can have surface modification like plasma treatment, or you can have hybrid cost effective solution like polymeric and ceramic material for industrial application. Now, I was telling you something about this transport mechanism through the membrane. Now, what are the way the membrane diffuses through any porous membrane or any dense membrane? So, transport mechanism, as I was telling, that there are mainly you have a active transport where the hydrogen molecules or the water. So, this is basically they are showing here porous membranes. Porous membranes are for more application towards the liquid purification system. So, in these porous membranes you can have active transport like this, that the contaminant or the water molecules, they are transported as it is, or they can attach themselves with another molecule and being transport. They can have all together they can go inside. So, you can see a little bit of partial or full pore blocking. So, these are some of the transport mechanism of the fouling mechanism or the transport mechanism through the porous membrane. But in dense membrane things does not happen like that. Dense membrane, like which we should use for this kind of the like hydrogen application, where the transport is purely by diffusion. There is very little effect of convection through it. So, we do not have pressure gradient onto two very strong pressure gradient onto the two sides of the membrane, permeate side and the retentive side. What we have is that mainly diffusion by the help of the hopping mechanism or through this vehicular transport system. So, that is the dense mechanism. Hydrogen only diffuses through a membrane like this. So, hopping, as we know that hopping mechanism is like we have different functional groups onto the sides of the polymers, and the hydrogen, the polymers, and the hydrogen proton, they just come and sit and they just jump on that. So, this is called the hopping mechanism. This is purely a diffusion variation. Or we can have vehicular transport, is that the water molecule is getting transported, this water plus H plus, they are getting vehicular, so water molecules is carrying the protons with it. So, these are the diffusion mechanism through any kind of such dense membrane, whether be it a composite or whether be it a purely polymeric membrane. Okay. Fueling station. So, fueling station also membranes can be used. So, we can use composite membranes also for this type of membrane, or you can have metallic membrane, which is more common in this case. So, where they are coming in picture? So, in the metallic, in this case what we do is that in the fueling station is that we have the many hydrogen powered cars are coming in market. So, for that at the fueling station what we see is that during the fueling, here at the nozzle we have some particular membranes installed, so that they can have a selective transport during this case. Okay. So, what are the challenges that we should be benefited or we should be keeping in mind? Because durability, if it is not durable or if it is at least 1000 cycles it should withstand. Otherwise, this frequent changing of this durability can be a problem in this case. Okay. It should be economical also, and hydrogen purification because we need a very high standard of hydrogen purity level. So, that is why these kind of membranes are used in this type of operation. We have to be very careful about the pressure, because if there is a leakage in hydrogen during this refueling, what will happen? A very big hazard. So, do you know about any regulation about usage of mobile phones in petrol pump? You know? So, why do they stop you from using the mobile phones? So, what is the reason? A static charge? Yes. So, actually what it used to happen earlier is that because of static charge, some of the mobile phones, because of heating and many other issues, there were some incidents in petrol pump that they used to catch fire. Okay. Now, imagine what if that regulation has come into picture because of why this risk of catching fire with this heating of membrane or static is there, because there are some vapor of petrol, vapor of gasoline roaming around in actual petrol pump. But imagine if there is a leakage in hydrogen container and you have heating or you have a spark in your membrane, what will happen? Everything will go like yes, boom. So, that is why we should be very much careful about this purity level or this hydrogen production system. Okay. Now, there are some advantages, as we have told, that you can have very high purity of your system, you can have very compact and scalable operation, lower operating cost. But the challenge that remains is that we have to have more durable membrane. Zirconium is good option, as I was telling, but we need to have more durability in order to have a more widespread application. You have to be careful with the permeation rate also. Permeation rate has to be a optimized level, because too high of a permeation or too low of a permeation, both are causing a problem. We can have a high initial cost. High initial cost can be using palladium to a high quality. It is getting the cost to be very high. So, we have to find an alternative to this kind of solution. So, that is why scalability concern is also there. We can have, so next I am coming to the question like how to select your membrane. So, we have talked about many types of operation, many types of compositions of our membranes, but the main two factors that come in picture are the selectivity and permeability. Palladium silver based membranes, they give you very high selectivity. Zeolite membranes comparatively less but still good. Polymeric membranes selectivity is comparatively low. So, these are some of the membranes that are most commonly used for these kind of operations. But permeability of these polymeric membranes are practically very high. So, they are basically counterintuitive. When you have a high permeability, selectivity goes down. When you have a high selectivity, permeability goes down. So, but both the things are important. So, you have to find a solution between the, we have to find a solution between the balance. Okay. So, that is why when we need very highly permeable solution, then we have to choose on which type of permeability we need to use or which type of membrane material we need to use for this kind of membrane. Now, what are the temperature conditions that we use or pressure conditions that we use? We have been talking that we require less pressure, we require less extensive, less extreme temperature. So, zeolite and MOF membrane you can use up to 250 degrees centigrade, but for palladium membrane you can go up to from 300 to 600, or polymeric membranes are something which you can be more relaxed with the temperature, you can go up to 150 or 200 degrees centigrade, no problem. But pressure is that inorganic membrane or inorganic alloy membrane, they can withstand very high pressure. So that is why these alloy membranes, they can withstand up to 30 bar without considering or without affecting the selectivity of the membrane. MOF based membranes also has, or composite membranes, they also have lower pressure selectivity. So if you want to reduce the selectivity, or if you want to reduce the pressure requirement of your membrane, you can have MOF polymeric composite membrane without compromising with the efficiency. If you have if you do not want to consider, or if you do not want to reduce your efficiency of the membrane but still want very high thermal stability, in that case porous ceramic membrane can be one good option. So now energy efficiency, what is energy efficiency? Basically energy efficiency is how much energy you need for producing of 1 kg of hydrogen. For membrane, we have seen that it is considerably higher than other conventional technologies, but this efficiency can go down given to some specific conditions. Like if the factor is affecting the factors that can affect your energy efficiency, they can be high permeability, or if there is any sudden change in operating condition, or if you are changing the material properties like that. So for that, what are the typical properties of the membrane that we should use is that when we are having very high pressure operation, we should use the metal based membranes. And now what are the strategies that we can use for this? If we want to enhance, or if you want to enhance the mechanical stability, more inorganic material should be incorporated, more process optimization, it should be generating minimum waste. So these kind of strategies we should be efficiently operating. Now in terms of fuel cells or hydrogen generation efficiency, we have been able to reach the efficiency of 60 to 80% in the range for the PM category, but this is again subjected to various operating conditions. So in order to enhance, or in order to have a widespread application of this technology, we need to further work on the stability of these membranes so that we can enhance the efficiency. Now what is durability? I was initially mentioning in a study that we go for different testing of our membranes, like whether it is durable or whether it is losing its property or under various cycles in a long term. So these are the tested or durability that we test in lab, but in real life that we can have the reduction in durability, we can have reduction in durability due to many aspects, like that thermal stability, if there is a high temperature gradient during the operation, or if there is exposure to some chemical, then our durability goes down in real life. Or you can have again, for increasing of durability, you can, other than the composite deposited onto your membrane as matrix, you can have protective coating, protective or insulatory coating on the membrane surface. Okay, and you can have structural reinforcement, like say in kind of metallic materials or all into infaced into the membrane materiality, so that the durability can be improved. Okay, so safety aspects. We have talked a lot about the flammability of hydrogen. We already told that even 4% of hydrogen mixed with air, that catches fire. So, but that we have talked about that if there is a tiny leakage, so membrane with leakage or membrane with defect, it is not at all allowed for this kind of operation. One problem that we have not talked about is hydrogen embrittlement. Okay. So when we are storing hydrogen in any membrane based container or any other condition, one thing we must keep in mind, hydrogen is very reactive also. So if it is very reactive, then what it is doing is that it is creating lot of reaction with the surrounding material, and the properties of the material, they change. The mechanical strength of this material or this reaction product they change a lot, and that is practically in gist what is embrittlement is. So with a long or prolonged use, we have to be careful whether the mechanical strength is being lost or not. Thermal stability is that for if there is any very high contraction and expansion of our metallic material, then also some cracks or defect can occur onto your membrane surface. So that also has to be thermally stable, like thermal expansion should not be very high for this kind of membrane. Pressure variation, also the pressure coefficient variation, it should be minimized, and that is why we have to have some mitigation strategy like periodic testing. We can have some composite materials, or we can have regular monitoring of the temperature and the pressure system. So cost analysis is mainly the cost analysis or cost comparison of among the different membrane materials are mainly same as like we were talking about yesterday. We can have lower cost with the polymeric membrane, but we have to be careful with other operations. But what I want to have a view is that this cryogenic storage cost around $5 to $10 per kg of hydrogen, but membrane based storage it costs around 3 to 7 per kg of hydrogen. So that is one that is much that is lower than the cryogenic, but compressed gas storage, that is that it requires that compressed hydrogen cylinder, or that it requires very although it gives you lower cost, but it requires high storage space, it requires many safety regulations, etc. Environmental impact, of course, it gives you lower carbon footprint, it gives you lower amount of waste and material. But one thing we have to be careful is that if our membrane materials are spent, whether they are safe to dispose to the environment or not. So there are some safety protocols which we will be talking about in our in my last lecture. So some safety protocols we have to keep in mind whether they are safe for discarding in the environment. And also we have to be careful about whenever we are installing any hydrogen storage system, membrane based system or otherwise, we have to be careful about the whether there is any hydrogen leakage happening or not. Now let us see some of the industry case studies, whether these membranes has been really applied and proven to be useful. Okay. So there are two companies, Air Liquide and Linde Group, where they have used hydrogen separation by using a palladium based membrane. Linde Group, they are a German company, they have these deploys polymeric membrane for hydrogen refueling station. Refueling station, they have used this in real life and they have got successful results. In aerospace, I was telling that NASA is implementing cryogenic membrane system for storing of hydrogen. Boeing is also doing the same, and Airbus, they are having these kind of different membrane based technologies for the future hydrogen aircraft. So these Airbus and Boeing and NASA, they are not applying it in a large scale system, but still it is in testing system, but they have proven or they have given much good results. Anyone is interested to buy this car, Toyota Mirai? What is so important about this car? So it is going to come in Indian market very soon. This is a hydrogen powered vehicle, which is which will be using a hydrogen fuel storage system in it. So in this system, what they were going to use is that this Toyota company, they are going to use is that they are going to have a composite membrane inside the connection between the fuel cell and the hydrogen storage tank, okay, inside their car. So in this they have a very very high means high reduction in the cost of this car. So that is what they are claiming. So this Hyundai is also working on such kind of membrane, and they are also we can expect some of this solution from Hyundai also. Other than these, you can have application in maritime industry also. You can have, we are seeing its application in heavy duty transport, and industrial manufacturing. Siemens is using ceramic membranes because they are using it for electronics purpose. And chemical and petrochemical industries, Shell and BSF, they are also using hydrogen, and they are having membrane based systems for the hydrogen storage and refining. So these systems I have already talked about the first two. In the Japans, they are also having a palladium alloy membrane, which is giving you hydrogen based, they are making energy and giving it to the energy grid. Okay. So if we have a look on the recent developments, or what is the future of these membrane technologies. So apart from the nanostructure membrane and composite membranes, we are also looking into the AI driven membrane, the smart membranes. What are those? That if there is any change in the surrounding condition, then the membrane itself will change its properties. Okay, it will change its properties and will its efficiency or its pore size or its control will be differently tuned. So that is what AI driven membrane design is being very much popular nowadays. So a lot of research is going on. Apart from that, most of the materials, most of the considerations are into the material consideration, so that you can reduce the cost and we can reduce the complexity of the systems. Okay. So these are some of the future trends like hybrid and smart adaptive materials, MOF based technology, or membrane based hydrogen transport, which we can expect in different temperature in coming technologies. So I was briefly mentioning about the smart or nanostructured material. So one of that I was telling that they adjust their permeability and selectivity based on the environment. So like for example, these particular MOF they have reduced by using of this AI. One particular paper in here, they have shown that these particular MOF they can reduce your energy demand by 7% reduction in energy demand by just using the AI based technology, by reducing its or tuning its permeability through it, which is an interesting concept because you are using the same material and you are practically giving it command to change itself because of there is a change in the environment. There are some purity standard, like same purity standard for this storage system also. So in the international hydrogen purity standard are like ISO, ASTM standard, and fuel cell vehicle has some industry specific standards, and aerospace and semiconductor industries, all of them require almost 100% purity. And membrane based technology for hydrogen purification, it is that they have they can have very almost 100% purity of these membranes. So government has taken up some policies and regulations. They have been giving different grants in United States, Japan, and recently in India also we have the National Green Hydrogen Mission, where they are employing more and more focus onto the large scale hydrogen generation and the hydrogen utilization. So that's all about the storage using membranes. If you have any question, please feel free to ask. Yes. Thank you.
How do you prevent the desorption of hydrogen stored in the membrane? Is it only dependent on temperature and pressure, or is there factors also?
Yes. So if we are not changing any other thing, just by changing temperature, you can control the desorption. So practically, if you see that it is an endothermic process, if we have a absorption process. So when we are controlling the temperature, so then we can actually switch between cycles by reducing the temperature and increasing the temperature. That is one possibility that you can do. Other than if you are trying to keep the temperature constant but want to still switch between cycles, then you have to use different materials mostly. So temperature is mostly sensitive, very sensitive for hydrogen absorption and desorption cycle, or otherwise pressure. Yes, pressure has a effect. You can switch different low pressure operation and high pressure operation to switch between cycles of absorption and desorption also. But in that case, if you change the material, then obviously you can have an absorption and a desorption, two separate system in a cyclic process. That is also another option that you can have.
Ma'am, here in this palladium based membrane, so different compounds are having hydrogen. So every time, how do you optimize your membrane thickness or the amount of what is the area of membrane you need for specific amount of hydrogen output? So different components it might change. So how do you optimize that? Means like you have shown one compound, so other compound is also having some hydrogen. So if you use this membrane to separate or store, so again these properties change continuously, or these are like some baseline for any?
Basically, which type of this answer depends on which type of mixture we have.
That is what. Ma'am. So every time it changes. I'm asking you.
No,
For depends on application.
Yes, yes. So it is practically, let us say that I have a mixture of carbon dioxide, carbon monoxide and hydrogen.
Yes.
So carbon dioxide, carbon monoxide and hydrogen, and so palladium will only transport hydrogen selectively. Okay. So that's why, so if we have the composition changed in carbon monoxide and carbon dioxide, it is it is expected that the efficiency or the transport or the flux or the permeability, permeability itself will not change of the membrane, but the total flux we might see a change because it is a operating pressure dependent, because the total driving force will be changed in that case. Okay,
That is what my question is. What is the, because if the material changes, the driving force may change.
Driving force may change, but permeability itself is a specific property of the membrane.
Okay, so so there won't be any reactions with the palladium even though if you use different types of materials also?
There will be a difference, that's what I am telling. Permeability will be remaining same, but effectively the
Life cycle may get reduced.
effective flux can be different. Effective flux of because in metallic membranes are comparatively more regular in structure. So that's why it is easier to maintain the permeability of the metallic membranes. But at the same time your driving force is changing because you are changing your composition of the gas. So in that case, obviously you can change.
With respect to the saturation of membrane, how do you know that it is saturated? Means like, for me, I am using for air dehumidification purpose. So I am using 1 desiccant, and opposite side I am sending my dehumidified air. So at one point I know that the membrane is saturated. So it won't, because of this hydrophilic nature or something, it will get saturated and it may not allow the vapor to pass through again, to absorb the vapor and send to the desiccant. So in this particular, how do you know what method you use to check for the saturation?
Basically, the guideline is to check your permeability after every cycle. Okay, so if you are working on the membrane field, then you must be knowing that after each and every cycle there is a washing protocol or there is a regeneration protocol. So after this regeneration and washing protocol, we generally check the permeability of the membrane. It is often not possible to regain the initial permeability. So there is a loss, maybe 10% loss at one cycle, another cycle maybe 5% loss. So if the loss in the permeability is too high, which is not acceptable for your specific condition, then you can say that the life cycle is over. So it can be very much application specific for the case. Okay. So what is application specific is that for your application, what is the amount of contaminant that you can allow in your treated stream. That is actually the main deciding criteria. Yes. Up to which you are reaching within you are remaining within the limit.
Thank you.
What's the fabrication method generally used to this hydrogen membranes, like to enhance durability?
Yes, yes. So, actually for polymeric membranes, as I was once mentioning that for polymeric membranes, when we are using this solvent non-solvent method, it creates pore volumes of a larger size, which we do not require or which we want to avoid in this kind of hydrogen separation application. So, in that case we need very thin or very dense material. So, one of the technology that we can do is that by evaporation of solvent. Okay. So, by casting, after casting we keep it under vacuum or at a inert temperature, that is the one possible solution. Other possible solution is that like sintering of the membranes, sintering of inorganic materials, which will give you more dense structure, okay, basically that are used for inorganic materials, okay. Or you can have coating of your membrane onto a surface, okay. I was showing once in a palladium coating method being used in a rolling machine, okay. So, these are the some of the economics which we have to keep in mind that the pore size should be minimum as possible. It should be thin and it should be also very low porous.
One more question related to that purity. Suppose if I am not able to maintain that 99.9%, so can I use that type of product also for other type of membranes? Like is purity is all depends on basically the poisoning of this carbon monoxide and sulfur only or any other?
No, actually when we are having this PEM fuel cell or others, then we need a very high purity of hydrogen. But hydrogen is not only used in energy application, they are used in as a reactant in many other places also.
For example,
Obviously.
for refineries we use it as one of the ingredients.
Yes,
For example, in
yes,
refining
exactly. So, in that case maybe 10%, maybe 90% purity level is acceptable. So, that is there. So, we can have sequential membrane process to enhance the purity of the level or other process like that. Okay.
Also material construction, how it is different from these cryogenic and compressive basic techniques. Like we use different type of materials. As you mentioned in one of the slides, the cost reduction happens with respect to this membranes utilization compared to the cryogenic cutoff. But in cryogenic, I think most of the time use alloy based materials. Is it costly or is it reducing cost in membranes kind of a technique?
In cryogenic, I showed that in cryogenic we use the membrane only at the exit part of the from the tank actually. So, membrane what it is doing is that if we have a membrane which can selectively allow hydrogen, then instead of storing pure hydrogen we can store a mixture. So, that is what I was telling. So, you can use pure palladium, obviously if you have alloy it will reduce the cost.
And one more problem with respect to this cryogenic things, a rapid phase transition happens. Inside that liquid converts to vapor, then vapor converts to liquid. So, because of that temperature and pressure fluctuations are there. Is there any kind of a problem associated with this membrane kind of a technology? Membrane, by using these membranes, there is a pressure, and you shown some of the slides, there was a temperature effect also there and pressure also, like continuously variation with the pressure, the amount of flux also varies, particularly with respect to some of impurities if it is present.
Yes.
That affects
It does, it affects, obviously it affects.
With prolonged usage, the mechanical strength of the membrane will it gets damaged.
Embrittlement, that is called
So
embrittlement.
the volume of the storage capacity also will decrease, right?
Yes, embrittlement has not only storage capacity, it has a risk factor associated with it.
Like if we suddenly, if we just put the same storage and there is like spoil of the membrane, then it might lead to explosions also. So that we need to consider during.
Yes, obviously. That is one of the, I have shown some safety regulations. This is one aspect of the safety regulations, that how much, at what condition it does embrittle. Okay, at what condition it breaks, it loses mechanical strength up to a certain point. So, these are all testing procedure. Okay. I will explain more about these safety regulations in my last lecture. So, it is like very, very important, especially for hydrogen energy. Yes.
Ma'am, you have discussed about metal organic framework as well as geolite imidazole frameworks for this membrane technology. Why aren't we using this COF, like covalent organic frameworks, often in this? Because they are more rigid. We can also, control the thin and thick layer, and as well as we can, tune the pore size as well. Why aren't we using them like COF? I haven't seen any.
Why am I not using
No,
POF?
no, I didn't see any application of covalent organic frameworks in this membrane. So I was curious, like whether they are, used in these particular membranes or not. I don't know.
Can you speak again, or maybe your AI is not clear?
Like I am asking, like
No, which term you are using?
covalent organic frameworks.
Polen organic framework.
Covalent.
Polen organic framework. I think they are still in the development stage. They have not been tested very widely in membrane technologies till now. They are still in the material development stage in the because if before using it for membranes, we have to ascertain certain properties, whether they are stable, whether they are mixable with these polymers and all. So I have not yet. I might be I need to expand my search field, but I have not yet encountered any reports onto membranes mixed with POF. I did not see it anything. Probably they need more research onto this kind of into this line. That's all. Yes.
Usually they are very unstable materials.
Yes.
They quickly oxidize.
Yes.
So how are they being used for?
Where did I mention? Did I mention in the ceramic?
Ceramic. That's okay.
In the ceramic.
In the metallic.
So I think I have mentioned it with as a material for alloy.
Okay.
As a material for alloy. So they can be like a material for a inside layer.
Okay.
Okay. There should be a protective coating above it, obviously. So perovskite, whether they are unstable, but at the same time they offer a lot of mechanical strength and the thermal stability. Yes. So that's why they can be used as a composite material, not as a sole membrane. Obviously, for the reason that you have mentioned, they are not stable, not stable when exposed to the hydrogen. So thank you all for your attention. I now hand over to Professor Vedanpur for the next session. Sorry, it took more time.
Please play video 4 before beginning. This is the hollow fiber production line. We have an injection pump for injecting the polymeric solution. Fill the cylinders for injection. In hollow fiber, we have bore fluid. That bore fluid should be inserted in the spinneret for precoagulation and producing of the hollow fibers, like a tube. This is the injection pump. We see similar to the nanofiber production. we have two pump, one pump for bore fluid, one pump for polymeric solution. This is polymeric solution, have viscosity. Previous one was water, no viscosity. We can control how many milliliter per minute the bore fluid or polymeric solution can be injected. We can control the pressure of pump. As you see in here, it is better. Began the fibers production, give with hand. Usually about 20 meters will be waste. Now this rolling can strengthen the membrane. The speed of this rolling is important. With the increase of the speed, we can reduce the size of the hollow fibers. Okay, go to PowerPoint. We say that we have many parameters should be controlled in the fabrication of membranes with phase inversion. In this slide, we show the effect of solvent. With change of the solvent, the porosity, flux, reduction, all can be changed because with change of polymer, with change of solvent, with change of temperature, the viscosity of the casting solution can be changed and cause to the change in exchange rate. In this slide shows that the slow exchange rate and fast exchange rate how can cause in the different mechanisms. With the phase inversion, we can produce spongy and finger-like membranes only with change of the polymer and solvent. In this slide, our polymer is cellulose acetate, and with change of the solvents, all of these solvents can be dissolved the cellulose acetate. The concentration is similar, 15%, but we see that the DMS or NMP, DMF have the high membrane water contact or porosity. This shows that in these solvents we have the high porosity, but in these solvents we have a low porosity. And we have a solvent solubility parameter I will discuss about in the green solvents in the 4-day. Every solvent have a solubility parameter, and this solubility parameter can cause that one polymer can be dissolved in this solvent. With having of the solubility parameter, we can predict that a solvent can be dissolved, a polymer or not. I will discuss later. You see that with increasing of solubility parameters, the porosity of the resultant membranes increase, and with increase of solubility parameters, we have a rapid precipitation, and with rapid precipitation, we have a high porosity that goes to the high flux. The thickness can be also influenced in the membrane. Generally, we know that the higher thickness can reduce the flux because the mass transfer will be related to the thickness. But the morphology of the membrane also can be influenced with thickness. When we cast the membrane, the casting liquid, with lower thickness, we have obtained a spongy structure. Our solution is. But with increase of the membrane thickness, we see that we can produce the macrovoids. Therefore, the thickness of the casting also can influence in the membrane structure. The coagulation bath temperature can be influenced. The non-solvent composition. In most cases, we used pure water, okay? But we say that when the polymeric solution come to the water, the solvent go to the water, okay? And after 10 minutes in the continuous production of the membranes, our water, our non-solvent is not impure, is not pure. Because the solvent come to the water and we have 1%, 2%, 3% of the solvent after 10 minutes. Therefore, in industrial state, we have not pure water as a non-solvent, and we have 2, 3, 4% of solvent. Therefore, we must investigate the effect of the solvent as an additive in the non-solvent. In this study, with use of the non-solvent as a 2-butanol, pure water, mix of water and isopropanol, and mix of water and butanol. We see when our non-solvent is 2-butanol, the morphology is spongy mostly, with a finger-like only on the top layer. But in water, we have a very porous, but in the mixture, we have a low porous. Therefore, the composition of non-solvent and inserting of the solvent to coagulation bath can change the morphology, and the morphology influence on flux and separation. Air humidity during the casting can influence. In this study, this diagram shows the humidity influence on rejection and pure water flux. We see that with increasing of air humidity, the flux increased, but the rejection very low decrease. With increasing of humidity, our process from non-solvent can be changed to the VIPS method, vapor-induced. In vapor-induced method, I say that we have a NIPS, IPS, TIPS, VIPS. In the VIPS, vapor-induced, after casting of the membrane, we put the membrane in a chamber having vapor. When we have a high humidity, like as India, now I think we have a 80% humidity in weather. But in Iran, we usually have 20 humidity. In Istanbul, 30, 40. Okay? Therefore, the fabricated membrane in India will be different from the Iran if we do not control the humidity. Therefore, the humidity, you see that with increasing of humidity, the flux increase and the rejection slowly decrease. And we see that SEM image of these membranes with high humidity, we see this, we have a very big pore size. But in medium humidity, we have a narrow pore size. For discussion about the exchange rate, phase inversion, and what happened during the solvent exit and water entrance and exchange rate, we used phase diagram. In the phase diagram, we have a polymer that dissolves in solvent. Okay? And when we prepare a casting solution, for example, 20% polymer in solvent, we have located in this area, this typical casting solution composition. This point will be located in this line. But when we, after casting of the membrane and put it in the non-solvent, that water comes to the solution and solvent exists. Therefore, this point began go to the left. And we have a movement of this line, and when reached to this place, that the final membrane, in this place, we have not solvent, and we have a polymer and non-solvent, and all porosity of the membranes will be filled with water, and all solvent will be removed. We have some areas in this diagram. We see this is glassy region, this gel region, and this one phase uniform region. Okay? For preparation of membrane, we usually prepare the solution in this area. In this area, we have a stable solution. That means when we have 2%, 3%, 5% of water in the polymeric solution, the polymer solution is stable. With addition of 2%, the polymer solution do not change to the solid. Okay? But with addition of the water, when we reach to this line that is named binodal boundary, the stable polymeric solution start to unstable, but not completely unstable. We say metastable. It is the between unstable and stable. This white area is stable, this gray is metastable, and this area is unstable. When the composition reaches to this area, the liquid will be solid. In this area, we have a solid membrane. In this area, we have a turbid area. As you see in the video, first, when we put the membrane in the water, the color is changed. And the film first turbid, and next become white. Okay? This is a stable, a metastable area. And you see that this area white can be different. In this, when we have this solution, this go to the right, reach to this area. When we have this concentration, this reach to this area. That means the white of this area is different. And this metastable, in most cases, produce the morphology. And with change of the composition of the casting solution, we can change the metastable region area width, and this goes to the membrane final structure. After addition of the most non-solvent, we have reached to the spinodal boundary. That spinodal boundary is the boundary between solid and metastable area. After spinodal boundary, we have a membrane, solid membrane, and we give time that this point reach to this area for production of a membrane. All of these diagrams, these lines, have a thermodynamic and kinetic equations. And you find one book about thermodynamic and kinetic of phase inversion. Some scientists also study in the kinetic and thermodynamic change in the phase inversion and draw this diagram. For drawing of this diagram, usually titration is used. We have a polymeric solution. 1 drop water is added, good mixed, and with the light, the turbidity is measured. When reached to the solution is turbid, but now is liquid, we reach to the binodal area, and when we add the final drop, that after adding and mixing for 1 hour, the obtained solid is not redissolved, we reach to the spinodal line. Therefore, for drawing of this diagram, maybe we need 2 months time. One student in their thesis, his thesis, 2 months every day should be prepare solution with different concentration, and add drop to drop water. 1 drop add, drop is solid, but 1 hour is tiring to complete dissolving of 1 drop. Again, 1 drop, 1 drop. 1 day for 1 point. 2 days, 3 days for design and drawing of this diagram. 2 months time is needed for completing. With change of the polymer, diagram is changed. With change of solvent, diagram is changed. With change of non-solvent, diagram is changed. Therefore, if we want to, for example, investigate the effect of solvent, we select 3 solvents. We must 6 months in lab analyze and test for drawing of the diagram. But this diagram is very important for prediction of the membrane morphology and why one membrane is spongy structure, why one membrane is finger-like and others that I have not time for more discuss. I go. For example, with change of D match and NMP, D match in the left and very difference in binodal line. This is binodal. With change of the very little in the white, we see that the D match and NMP have very different structure as seen in the previous slide. In this slide, we also can see that with change of the molecular, with change of the polymer concentration, we have a similar, different structure. There are 16 parameters for obtaining the membranes. In this slide, I show that in commercial UF membranes prepared from CSM coach Ami from India, Dow Film Tech, Hydronautics, Toray, where I go? Most used polymers is polysulfone, PVDF, cellulose acetate, acrylonitrile, polyacrylonitrile, and polyamine. Okay? As you see in the commercial UF, mostly polysulfone, polyethyl sulfone, PVDF, some cases PVC, some cases polypropylene. But PVDF and polysulfone is usual because of a high durability and good chemical and mechanical resistance. The second most used phase inversion is TIPS, thermal induced phase inversion. In non-solvent NIPS, we say that the non-solvent goes to the solidification. Okay? In the TIPS, we have a two category. One category is most used in high temperature, and a solvent can dissolve a polymer. For example, in 150 centigrades, a polymer can be dissolved, a solvent can be dissolved a polymer. But if the temperature reduced to 70, the polymer will be dissolvable, okay? Not soluble. Therefore, in this technique, in high temperature, we prepare a uniform solution, and in high temperature, we cast, and next, allow to reduce the temperature. When the temperature reaches to 70, solution will be changed to not soluble, and phase inversion happen, okay? With reduce of the temperature, the solubility is removed, and a soluble solution will be changed to the unsoluble, and we no need to the non-solvent. And this named as a thermally induced phase separation. Therefore, in the low temperature, we have a immiscibility. We can use PVDF polyethyl sulfone for this purpose, but the used solvent is different. In NIPS, we use DMAC, NMP, DMF, DMSO, but in the TIPS method, the solvents are changed. We use dimethyl phthalate, diethyl phthalate, dibutyl phthalate, dioctyl, all of the phthalate groups, and all of these solvents is oil. This most use of, for example, DOP is used as a stabilizer in the PVC for flexibility, increase of PVC. Okay, after preparation of PVC tubes, usually 2%, 3%, added DOP or DPT for increase the flexibility and reduce the brittle of PVC tubes. But in this case, we dissolve PVDF in DOP, DBP, and in room temperature, DOP cannot dissolve PVDF. For dissolving, we need high temperature. After high temperature, we cast the films and allow to decrease the temperature. As you see in this diagram that is named upper critical solution temperature, such as PVDF in DOP, we have an unstable regime and stable, okay? In high temperature, in this area, for example, in 150 centigrade, we have a single phase and stable solution, but with the reducing of the temperature, we come to the unstable area. And in this area, this is a binodal. In this area, the phase inversion happen and the liquid change to the solid. Most of the tips in this method, but we have some solution with reverse behavior. We say reverse tips. Some solutions in low temperature is soluble, with increase of the temperature is non-soluble. Most of polymers have this behavior, but some solvent and some polymers have this behavior. Mostly with change of solvent, this behavior change. Therefore, in reverse tips, in room temperature, the polymer can dissolve in solvent. We cast the film and increase the temperature. When reached to 100, liquid change to the solid. Therefore, in this case, we have a LCST. We see upper CST, critical solution, and lower. Most we have this process, but in some cases we have this behavior. The prepared membranes with the tips have larger porosity and uniform pore size. The NIPS problem is that we have not uniform pore size. We have a wide pore size, one big, one small. But in the tips, we have a narrow pore size, and this reduces the fouling. You see that the polysulfone with NIPS, this morphology, but with the reverse tips, have this morphology. The effect of coagulation bath temperature on tips also important. After the solidification, okay, we have a film that have solid, but the solvent is here, and we must remove the DOP, DBT, okay? Therefore, after the membrane fabrication, we put the TIPS membrane in the coagulation bath for remove of the solvent from the prepared membrane. Membrane is prepared, is solid, but for remove of the solvent from membrane, we put the membrane in coagulation bath. Therefore, in TIPS, we have also coagulation bath, but this coagulation bath is not for solidification, only for remove of the solvent, okay? Therefore, after TIPS, we have a coagulation bath, and this show the coagulation bath effect in the membrane structure, that in lower concentration of the polymer, lower, the coagulation bath temperature can be effect, but in the higher concentration, usually have not effect. Therefore, coagulation bath also can affect on the efficiency of membrane in TIPS method. And the final method, VIPS, I say that in the VIPS, we have a vapor chamber, and we have used usually vapor of water for producing of the membranes. I say that with increasing of exchange rate, the pores is low, small. Okay, the next lecture, I say that in the exchange rate, when we have a high exchange rate, the pore size will be small. If we have a low exchange rate, the pore will be big. In the VIPS, we used vapor of water instead of direct water, okay? In NIPS, we put the membrane in water. The concentration of water is very high. But in the VIPS, we put the membrane in contact with vapor, that the concentration of the water is low. Okay, vapor is in the mixed with the air. Therefore, when concentration of the water reduce, the exchange rate reduce. Okay, when we use VIPS, the concentration of the water reduced because water is dispersed in air. We have a vapor, and this caused the slow exchange rate, and slow exchange rate caused to the big pore. Therefore, VIPS is used for fabrication of microfiltration membrane mostly. Okay? Therefore, VIPS used for microfiltration, because instead of liquid water, we used vapor water. The exposure time to the vapor and the vapor density or vapor percent is important. In these membranes, the humidity, relative humidity is 100. The air is saturated from vapor. When we say 100 relative humidity, that means that most of the gas phase is air, nitrogen and oxygen. And humidity, vapor, reaches to the saturation concentration. In this gas phase, in the vapor phase, 1% is vapor, and most phase is nitrogen and oxygen. You see in this one that with increasing of the exposure time, 10 minutes, 6 minutes, 5 minutes, 3 minutes, 0 minute, this, the morphology is changed. Therefore, exposure time and humidity is important. In this case, we see for exposure time also, and see that the morphology can be changed with exposure time. Okay, this presentation for
Also, check, okay. Hello. Check, control check. Check.
Okay. Good afternoon. In this section, we will have tutorial about the membrane characterization. After fabrication of membrane, the first work is the measurement of flux and rejection. Our students first test the flux, rejection, fouling properties, and other experimental tests before characterization. Because we have a setup in our labs, and we can, without expense of any money, and with a low amount of materials, we can test the membranes. But characterization needs money. And if we first characterize and next measurement the flux, maybe the flux result show that this membrane is not good. And therefore, the characterization is no useful. Therefore, after fabrication, we first test the membrane permeability, flux, rejection, and if the result is good, for explanation of that why flux increase, why anti-fouling properties is increased, for discussion, explanation, we characterize the membrane. For example, we say the reason for increasing of the flux is increase in pore size. For this sentence, we must measure the pore size for approving our hypothesis, and therefore we characterize the pore size, the morphology, and other properties of the membrane. The usual characterization of the membranes are listed here. And with the SEM image, we can see the surface morphology and cross-sectional morphology. With transmission electron microscopy, we usually measure the thickness of the TFC layer and presence of nanomaterials in the membrane structure. With measurement of porosity, we know that how many pores and free space there is in the body and in the surface. We measure pore size with atomic force microscopy. We measure the smoothness and roughness of the membrane surface. With zeta potential, we measure the charge of the membrane. The membrane is negative or positive, and if negative, how many negative? We measure the contact angle, water contact angle, and in some cases, oil contact angle of the membranes for showing the hydrophilicity. And for approving the functional groups in the membrane surface, we measure the ATR, FT, IR that I try to discuss in the next slides. Scanning electron microscopy is very expensive device that show the morphology of the cross-section and surface of the membranes. This is a microscopy that means large the size of the membranes and zoom on any area that we want to see. And we can see the porosity and shape of the pores. The pores is finger-like or spongy. How many porosity is there? We can see the pores. If the pores is big, we can see the pores. But if they're very small, in most cases, we cannot see the pores. And we can see the thickness of the membrane, how many thickness. And we can see, for example, the nanoparticles mixed with the membrane, in the matrix of membrane. We can find the nanoparticles in the membrane. Before SEM image, we should prepare the sample. If we want to give surface SEM image, we must clean the membrane. In the most cases, we have some particles, some microbes in the membrane surface. And when we give the SEM, you see this particle. This is a dirty. If we do not clean the membrane, there are many of these dirty in the membrane surface. Usually, we must wash the membrane surface first with distilled water, next with ethanol, and next with distilled water, and dry in oven, and go for gold sputtering, gold coating. This is a scanning electron microscopy. That electrons go to the surface and come back, and the detector see this electron. And for this purpose, the surface of the polymer or everything should be conductive. And for this conductivity, we use the gold, carbon, and palladium coating. And for this coating, we have a sputtering device. And with putting of the membranes in this sputtering device, we can coat a thin layer. We put the membrane in device, and 30 seconds or 1 minute, coat the very thin gold layer on the surface or on the cross section for producing conductivity and vision. The electron go to the surface and come back. Therefore, between the beam and the surface, we must have vacuum, no oxygen, no nitrogen. When we oxygen, the electron will contact to the oxygen, nitrogen, and we have no good resolution. Therefore, after putting the membrane in this chamber, we have a vacuum pump, and we have a very high vacuum pump. And after vacuumation, began to scanning of the surface. For seeing the cross section, in the surface section, we have not problem. Use membrane after cleaning. But for seeing the cross section, we must crack the membranes. We can use the, what is this? Scissor. For cutting, the scissor press and destroy the membrane. Therefore, we cannot use the scissor. If we use scissors for cutting the membrane, we cannot see the cross, and the cross destroyed. For this purpose, we must first change the flexible polymer to brittle polymer. For this one, we reduce the temperature with liquid nitrogen. We put the membrane in the liquid nitrogen for 10 seconds, 20 seconds. the temperature goes to the minus 100 centigrade. And in this case, with a little, what is, little snack, what you say to little pressure, this membrane will be cracked. Therefore, we first put the membrane in the liquid nitrogen, wait for 10 seconds, and we have cracked the membranes in liquid nitrogen, and due to the brittle one, we can see these pores uniformly. Therefore, we cannot use scissors for cutting the membrane. This is some examples. You see the morphology of the RO membranes have some nodules in the membrane surface. This is the fabric, non-woven fabric, that the polysulfone layer is coated on the non-woven fabric. But with the using of SEM, we can see the thickness of the membrane. What is the thickness? You see, we have a bar for showing the thickness. This bar shows that the thickness of this layer is about 70 micron. And we have a magnification. In this figure, we have a 1,000 magnification, 1 kilo X. Okay, 1,000 magnification. In this, we 6,000. In this, we 20,000 magnification. In this, we 35. Therefore, with SEM, we can have magnification about 100,000 X magnification. Okay. Therefore, with SEM, we can see these properties. Or we can see the pores. If the membrane pores is big, we can see the pores with use of the SEM. Or we can compare two membranes. With addition of this nanoparticle to the polymer solution, the resulted membrane have a smooth surface than this one. This is non-corrected Bayer membrane, but this is the corrected membrane with this nanoparticle, this carbon dots. And addition of carbon dots reduce the surface roughness, okay, or surface morphology. Or in this PVC membranes prepared by WIPS, we see that with increase of the exposure time to the vapor, the pores size is increased. Okay, this is small, this is some bigger than, and very, very big. Therefore, with use of SEM, we can see morphology, pore size, thickness, porosity, and very important test for characterization of membrane. Or with high magnification, we see that there is very small pores in the finger-like structure of the membranes. Another device for topology of the membrane surface. AFM used only for surface, not for cross-section. And we measure the peak and valley of the membrane, that named as roughness. How many roughness the hill and valley there is in the membrane surface. Usually the smooth surface have a good antifouling properties. But rough surface can easily followed by protein and other macromolecules. In the atomic force microscopy, that's similar this one, we have a very little needle that's named tip, with tip, and have two modes, contact mode and non-contact mode. Contact mode, that's this tip can be contact with the membrane surface, or in this non-contact mode, there is a nanometric distance between this needle and the surface. The electron goes, and the distance between the surface and tips is constant. And this electron in a microsecond go and back, and this top and bottom movement can be draw the membrane roughness. Therefore, in the membrane, we most use non-contact mode. For measuring of the roughness of membrane, we use non-contact mode. No need for sample preparation, only the surface of membrane should be clean. And as I said for SEM image, we clean with distilled water, ethanol distilled water, and give the operator for measuring of the AFM image. Taking of AFM image need about 20-minute time, because very low surface area scan and go batch. Usually 10 micron per 10 micron, 20 per 20 micron area is scan, and this scan of all of topology need time. Therefore, SCM is rapid, but AFM is a slow process. Usually, we have a two-dimensional and three-dimensional images from the scanning. You see in this two-dimensional, the scan area is 5 in 5 micron. And we see the pores. You see, this the black area is the pores, is the valleys, and the red area is the membrane matrix, and the white area is the peaks. These peaks can be mostly due to the impurities, due to the sands and other impurities. Okay? In some cases, this can be the added nanoparticles. We mix the nanoparticles in the membrane matrix, and we see these nanoparticles. We have see here two numbers that shows the most peaks of the height of peaks. And this shows this particle, this white particle, how many height from the surface. Usually, after scanning, the software of the equipment give many parameters to us. But in membrane science, we usually use these 4 parameters. And most important, this average roughness. This is average roughness that shows that this figure, what is the average roughness, okay? when we compare two membrane, one is average roughness 20, another is 30. We say that the 30 have higher roughness than 21. Okay? In UF, MF, we want to reduce this SA because with reducing of the roughness, the fouling will be reduced. And this SZ show the highest peak and the highest peak, you see, the highest peak. And SQ show the root mean square that can be calculated with this one. In some cases, the AFM operator give us R, RA, RS, RZ, RQ. When we say S, S means surface area. That scan all of this 5 in 5 micrometer. But when give us RAQ, RAS, RAA, in this area, we have a line and not surface, complete surface. And this is not good for us. It is better we measure the S. Okay? Request from the operator, we need SA, not RA. We need SQ, not RAQ. R is the measuring of one line. And so this is the RAS, the maximum peak. And this line is the RAA, average roughness. That average roughness of the valley and peaks. This is another AFM for RO membranes that you see that RO membranes usually high roughness. RO membranes have high roughness, but UF, MF, NF have low roughness because the preparation method is different. MFUF was prepared from phase inversion, but RO prepared from interfacial polymerization. That's different of them. And this is the equations that show that how calculate these parameters. Based on the membrane pore size and membrane type, we can suggest the scanning scale. In RO, NF, it is better this 5 to or 1 micron is good. But in MF, because we have a big pores, this scanning area is not good, and better in the MF membranes, we increase the scan area for showing the pores. As shown in this AFM, we see the pore, and one of the pore size measurements is using of AFM that I will discuss. Therefore, when I have a big pore, we must increase the scanning area. Any question about SCM and AFM? You say SEM or SEM? SCM. Some countries say SEM. TEM or TM? TEM is a very good device for showing the membrane coating layer, TFC layer, showing the nanoparticles present in the membrane. But preparation of sample is very hard. In the scanning and SCM and AFM, electron go and back. And we measure the backward electron. But in TEM, electrons should be transmit from the membrane body and go to the behalf of the membranes. Electrons should pass from the membranes. And therefore, the thickness of the membrane should be very low. And generally, the membrane have very low thickness, 100 micrometers. But for preparing of sample, there is a knife that cuts these membranes to 10 micrometer thickness, and need a special device and preparation of this sample. Therefore, most of TEM operators cannot prepare good samples, and therefore TEM image is not good. In our paper, mostly I do not use TEM because I give sample to the operator and give about 6,000 rupiah for one sample. But after giving the image, I see that image is not good. And my money go. Therefore, if the reviewer, I submit the paper, if the reviewer requested them, I have to give the TEM, and in 2 and 3 times send samples, and 1 is good. Therefore, the preparation of the TEM samples is very important, but you see, we can see very good images, and we can see the thickness of this polyamide layer, you see, and on the surface of polyamide layer, we have a coating of gold. And we also can see the gold on the surface of the polyimide and see the polysulfone. It's a very good image for discussion, our results, but giving of them very problematic. Another characterization is surface charge measurement. For measurement of surface charge, we have zeta potential device, like as this, that we have a clamping cell, like as this, that's located here, you see. Based on the device, we need 2 in 2 centimeter. In some device, we need 8 centimeter per 8, very big surface. But in new device, we need 2 per 2 centimeter surface area. And we locate the membrane in this clamp cell. And for measuring the surface charge of the membrane compared with the reference. We have a reference, mostly polyether ketone sheet, that is the standard of this device. And the charge of this polymer, this reference polymer, is known. And we measure the charge in comparison to the reference. For this, we change the pH, and in different pH, we measure the charge by an electrode system. Here, we see we have an acid solution, base solution. this acid solution go usually 1 minute under the surface, and with change of the pH, we know the functional groups can be changed. With increase of pH, the functional groups began to dissociation. When we have, for example, these groups on the membrane surface, okay, in the lower pH, in this place, some 4, the most of this group have a acid one and no charge. But with increasing of pH, this change to the negative 1, and therefore with increasing of the pH, the negative charge of membrane is increased. Usually in the papers, in the researchers, we prepare 5, 6 membranes, and we want that our correction, our modification, our additive, how change the charge. For example, in this study, 1% of boron nitrate, graphene oxide, silver nanoparticle will be have been added to the polyethyl sulfone, and we want to show that addition of this nanoparticle how change the surface, and we see with addition of this nanoparticle, the surface charge is more negative, and when the membrane have negative charge, this causes the most rejection of negative ions as Donan exclusion mechanism. There are different types of zeta potential measurements. For example, we want to give the charge of particle. We give the charge of wood. There are different types. In the membrane, we use streaming zeta potential. Streaming, that means that we have a fluid. That fluid can go from the membrane surface and change the properties. Therefore, we use streaming method for measuring of membrane zeta potential. For measuring zeta potential of, for example, nanoparticles, usually have different pH solutions and give the nanoparticles them for 1 day and mixing, and after 1 day began to titration. Based on the titration results, suggests that the membrane, that the nanoparticle surface charge is positive, negative, or how many positive or negative. Therefore, in the membrane, we use streaming zeta potential. In another study, we see that with increasing of these carbon dots, the surface charge of the RO membrane will be negative, and this negativity can change the membrane rejection. Usually, as a streaming fluid, we have a this solution. We want to measure the electrically conductivity of this charge, and for this we need the ions, and usually we have this KCl solution that with increasing of acid or pH or base, we change the pH of the solution. Therefore, we have this KCl solution for measuring of the streaming potential of the membrane. Another properties that's important, many important, hydrophilicity or hydrophobicity of the membranes. As yesterday said, that in membrane contactor, in membrane distillation, in hydrophobic pervaporation, we must have a superhydrophobic membranes. And in ultrafiltration, microfiltration, RO and F, we want to membranes have hydrophilicity properties. For measuring of this behavior, we must measure the contact angle between one water or oil with the membrane surface. We put, with this device, you see very little needle, about 10 microliters a drop on the membrane surface and give the picture, as you see in this. Membrane located here, one drop located on the membrane surface, this membrane, and from the side, we measure the picture. When we put the drop on the membrane surface, if the membrane is hydrophilic, the water will adsorb on the hydrophilic polymer, and therefore liquid wants to spread. But if the membrane has hydrophobic, that means do not like the water, therefore the water will not change, will not adsorb, and stay constant. Therefore, the face and the figure of the drop will not change. In hydrophilic membranes, after addition of the drop, after 30 seconds or 1 minute, all of the drop will be adsorbed and you do not see the drops. But in hydrophobic polymers, after 1 hour, you come back and see that the drop is here and no change. Therefore, we measure the hydrophilicity and hydrophobicity. When the water adsorbs in hydrophilic, the contact angle is reduced. Therefore, low contact angle show more hydrophilicity. High contact angle show hydrophobicity. Yes?
What angle are we measuring?
How measure?
Which angle?
We angle this one. This one. When this one, when we have a when we have this contact, this means that this have many more hydrophilicity than this one. When this decrease, you see, this show that this is more hydrophilic. For measuring of this area is very important and very challenges that how we can measure this one. You see, in this case, I draw this contact, but this true is this one, okay? Therefore, for measuring, we do not measure. The device measures this contact angle, and we have a baseline, and the contact, this area is important. And the contact between this baseline and this line is important, and the device measure this contact angle and say us. This is a report of a device. The software of the device report this. As you see, each second measure this contact angle. You can say to software only one time measure, for example, in the 1 second, but you can say that I want the change of the angle during of the time. Okay, this is better for report. That's named as dynamic contact angle. Dynamic, that means how the contact angle changes with the time. Okay, but in static, we only measure the contact angle in a certain time. It is better we report this one. As see here, here left and right. The software both measure the right and left of the drops and the report. And you see, in some cases, left and right is different. Okay, you see? But in the after 9 seconds is relatively similar. And this report the average. This M is the average, right, left, and this is average of them. Therefore, in the first second, the result is not suitable. And usually in static contact, we report after 5 seconds. Any question about? Another device is FTIR. FTIR is mostly used for characterization of functional groups in all compounds. And organic students, many use this device when synthesize a molecule, a compound. In FTIR, not ATR. In FTIR, an organic compound mixed with KBr, potassium bromide, and prepare a disc and used in a clamp in disc, and IR radiation, infrared radiation, pass from this disc and go to the detector. Okay? Therefore, 90% is KBr, 10% is our chemicals. And IR pass from these samples. But in the membranes, we have a film. And the IR cannot pass from this. Therefore, we use ATR, reflectance. Reflectance, that means, in this case, the IR go to the surface and back to the detector. In the simple FTIR, the IR pass and detector is here, but in the ATR, IR go and back to the detector, and therefore ATR, FTIR we must use, not FTIR. And this device is expensive than FTIR. Usual, the scan area of the IR is from 4,000 to 400. From 400 to 4,000 wavelengths. And the result of this FTIR is similar to this one. And pay attention, in most papers, write that 1,600 peak, and say that these are peaks. These are not peaks. This is absorption band, not peak. We must say that this is band, not peak. Peak used in NMR, UV visible, and other devices. Have a scientific discussion. I don't know why we say this band, but please use band, absorption band, not peak in discussion. With having of this diagram, this spectra, we say spectra, spectrum, spectra. With having of this spectrum, every of this absorption band shows a functional group. That's listed here. When we have absorption in this area, shows that we have a hydroxyl groups, for example, in protein, polyphenol, carbohydrate. Okay? Therefore, when we have this group here, okay, shows that this HEA have hydroxyl groups. Okay? And others. Carbonyl usually has in this area. When we see in this area, we can go that's the carbonyl. But when carbonyl is attached to the amide, fatty acid, or ester, can shift, red shift or blue shift. And this shift also can say that this carbonyl is attached to which compound. Therefore, with FTIR, we can find that the functional groups, and in organic chemistry, with having of FTIR and NMR, can predict the structure of the compounds. The organic chemist synthesizes a new compound with measuring of NMR, carbon NMR, hydrogen NMR, FTIR, UV visible spectrum, and in some cases, mass spectroscopy say that the chemical structure of this compound is this one. Other important properties in the membranes is porosity. Is porosity, that in porosity, we want to measure the free space of the membranes and have different techniques. The simple one is gravimetric method. In gravimetric method, we first weight the dry membrane. We cut a membrane with a certain surface. For example, 5 centimeter per 5 centimeter. Big surface, big membrane results in true results. For obtaining true results, use big membrane, not small. We have a big membrane, big area, the thickness, the density of water, the wet weight, and dry weight. The dry membrane will be weighted after keeping in water for 1 day. After 1 day, all of the pores will be filled with water, and you weight the wet membrane, and we say that the porosity completely filled with the water, and with measuring of the amount of water and having of the volume of the membrane, we can say that how many porosity is there in the membrane. In some cases that the polymer is hydrophobic, more hydrophobic, the water cannot good pass. In this case, we use isopropanol or another alcohol instead of water. Therefore, when we have a PTFE membrane, we use isopropanol. And in this equation, we use density of isopropanol. Here is density of water, but if we use the isopropanol, we use the density of other solvent. Another instrument for measuring pore size and porosity is intrusion method. Intrusion method such as BET. You know BET? BET. In the BET, we fill the free space with nitrogen. Or in intrusion, we fill the pores with mercury. And based on this filling of these pores, we can calculate the pore size and the porosity. With analysis of the AFM and SEM images, we can also calculate the pore size and porosity. When we have this SEM image, we know that these are the pores and these are the membrane body. Therefore, we give this picture to the image analyzer software, image processing software, such as ImageG, Fiji, Onyx, and others. ImageG is free. You can download ImageG and give your SEM or AFM to this software and request to calculate the porosity and pore size. You tell in the software that black area is pore, or in this area, black area is pore, and the red and yellow area not pore. And therefore, software calculate how percent of this surface is pore and can calculate the size of these pores. Therefore, with the image processing software, we can calculate the pore size and porosity. A simple equation and method for measuring mean pore radius, average pore radius, is this equation, Gerolf-Elford-Ferry equation. Okay? This equation, with the using of this equation, we can predict average pore size. Average pore size. That in this equation, for obtaining this radius, we need porosity, surface porosity. Okay? We must have porosity data, the water flux, pure water flux, applied pressure for this flow, the surface of membrane, again, porosity, and the excuse me, the thickness of the membrane, okay? For measuring of the mean pore radius in lab without any expense of money. We measure pure water flux in the applied pressure. That we usually measure the flux of membrane. We apply 2 bar and measure the flow of the membrane in the time. We have this. We have a membrane surface and we measure the porosity on the base previous method, and with this calculation we can predict that mean pore radius how. But have a high error. Some scientists not accept this method and say this method is not good and better you use BET or mercury intrusion. Another device that today most used is capillary flow porometry. Capillary flow porometry used for measuring the pore size distribution, porosity, mean pore size, and others. In this method, we keep the membranes in a standard solution. Every device has a standard solution. We put the membrane for 2 hours, 3 hours in this solution, and all of the membrane pores will be filled with this solution. Next, we locate these membranes in this module here, and we have a different size of the modules with different diameter, or this is for the hollow fiber. This is for flat sheet, this is for hollow fiber. After filling of the pores with this standard solution, we locate the membrane here and began to apply pressure. In the low pressure, the liquid do not permit to pass off the gas. We little, smallly increase the pressure, but we have not gas permeation because these liquids do not permit for passing of a gas. But in the special pressure, the biggest pore that have low capillary energy began, and the gas began to pass, and our detector detect the gas. This pressure is right. Is right that the first gas permeation shown in this pressure, and we increase the pressure to open all of the pores. Big pores first open, and the small pores the last. Based on this change in pressure, okay, we obtain this diagram. The red one is when we have no membrane, and with increasing of the pressure, this should be the gas permeability. Okay, but in up to this area, we have no flow because the pore is filled. But in this pressure began and increase, and in this point, all of the pores is open, and we obtain this diagram, and we compare this diagram with the standard one, and with comparing, we obtain the porosity and pore size. In the dictionary of the software, have that if the pores between this pressure and this pressure, the pore size is, for example, 20 nanometer. Okay, understand? I finished. Thank you. If any question, on time. There are another characterization based on the membrane type. Based on the, for example, for oil-water separation membranes, we use oil drops for measuring contact angle, okay? Not water. In this case, we use oil for showing the oil wettability. In some cases, we must measure the strength and tensile of the membranes. This polymer can be durable in the high pressure or not. In this case, we use the tensile measurement for measuring the stability and strength of the membranes. Therefore, based on the membrane type, maybe we have other characterization that's not usual. I speak about the usual characterization method, but we have a special membranes. We have a special characterization also. If any questions, I can discuss. Yes, yes. All of this characterization can be used for hollow fibers. No difference between flat sheet hollow, only configuration. When we say that hollow fiber UF or flat sheet UF, the chemistry and the morphology all is the same. The pore size, the porosity is the same. Only the configuration and the structure is different. Therefore, we can measure SCM of the hollow fiber, pore size, porosity, and all the same. Or for tubular, or for ceramic, all can be used. Professor Raka, I finished. We will go to the lab. Huh?
Thank you, Professor.
Thank you.
And so actually, what in the next session, we are going to show some membrane fabrication that is hands-on, what we have been learning about in the student lectures all throughout. So that we are going to show hands-on, and that will be in the new building of IIPE. So in the new building of IIPE is just basically around very short distance from there. So we will take a half an hour break. Will you please use this time to reach to the new building? I am going to share the location with you shortly. Okay. So location in the WhatsApp group. In the half an hour time. So now it is 3:30, right? 3:40. So around 4:10, we will be all meeting at the security, in front of the security of the new building. Okay? New building of IIT. We are going to share the location shortly with you. It is just when you go that side, it is just outside the